My experiences around biomass to energy, waste to energy technology development. The experience which I acquired while working in UK, some European countries and India. I make a start and inshallah I'll give you the chance to ask questions. You can ask me questions while we go along, as well as obviously there will be hopefully a session at the end where we can do question and answer.
डॉक्टर साहब we would appreciate कि क्वेश्चन जो है वो एंड पे पूछें ताकि जो कंटिन्यूटी ऑफ थॉट है ना वो कम से कम ब्रेक ना हो. We have a complete question and answer session at the very end.
Also, I have brought some samples so that it makes it easier to visualize things because when you're talking about some materials, some physical objects, tangible objects, it's very straightforward to understand when you look at the thing rather than me explaining virtually and I don't know, you might imagine something different. I might be saying something else. So I have some samples. Imran, if you can just move it around and make sure everything comes back. So these are samples of biomass and biochar, and there is another very interesting material which we also have the capability to process. This is called carbon fiber, the material which is used mostly in aviation industries as a super strong steel alternative and very light. So we have the capacity to recycle this material as well. So let's make a start because we have a couple of slides and you will be really locked in for a bit here now. So brace yourself for some information. So inshallah today we will obviously start the biomass waste types, processing technologies we will talk about. I will share my hands-on experiences of 3 different bioenergy systems which we developed in my career which spans over 15-17 years. And reactor design concepts, emissions, very important obviously everywhere, but very particularly in Europe, emission compliance is a major issue for any biomass to energy and waste to energy system. And gasification system configuration, torrefaction and pyrogasification, these are key technologies, let's say when we look at biomass as an energy carrier and storable material. Torrefaction is very important. Pyrogasification is another advanced thermochemical conversion technology I will go through. And there will be some takeaway messages from my experiences and then we will finish. So types of waste, and when I say waste, I'm not just only limiting ourselves to biomass. There is a lot of biomass in municipal solid waste. Typical composition is about 40 to 50% organic or biomass in the municipal solid waste, which is normally sent to landfill, and we think of it as a smelly, unwanted material. In fact, this is another resource which can be converted into energy. So there are various different types of waste residues and materials. Residential, obviously you are quite familiar with the black bin bag waste, what we call it in Europe. Normally things which you put in plastic bag and throw away to for the municipal authorities to collect and dispose of. Likewise, we have industrial waste, commercial and institutional waste, construction and demolition waste is another very big industry that produces this type of waste. Medical waste and agricultural waste, and I think in today's setting we are mostly looking at agricultural waste, and this is the kind of material made up of all sizes, all types of straws, husks, and a lot of sugarcane bagasse and wood shavings and a variety of things. You must be familiar with a lot of these yourselves, are it? I don't want to go in very detail of this, but what I'm trying to highlight here is the calorific value or the gross calorific value. This is the amount of energy which is released when you combust any type of material. So this is an excerpt from some sort of literature research, and it highlights or tables a variety of materials and what is their minimum and maximum velocity value. And if you look very closely, you see that heating values are around 15 to 20, maybe 22 is one of them at the very bottom. Carbon plant doubles. When we say season, we have a lot of oils present in those things, and that's why the calorific values go. So, in summary, we are talking about materials which have considerable calorific value, quite comparable to coal or lignite coal, and this opens up the door for us that we can potentially use these materials in coal-fired power plants, but also as standalone material in a lot of different technologies which we can go through in. So this is a bit of research, again, not my own, we have done some research ourselves. Here we try to calculate how much biomass to energy potential or how much biomass to energy is possible in Pakistan. So the key takeaway is at the very bottom, 9.51% of the energy requirement in Pakistan can be met by using these biomass resources. Okay, so I will try to mix up a little bit to inshallah. So अब है कि all these materials are available in different regions within Pakistan, different cities, different rural areas, and this is one of the key issues with the biomass. It's not available in one place, it's segregated, and collection has a cost attached to it. One key material which I highlighted here, this is from one of our projects which we are doing here in Pakistan. This is the banana waste, and here we highlighting how much banana waste is available. And when I say banana waste, I'm not talking about banana peels from the fruit. I'm talking about the stem waste. The stem, which is nearly 95–96% of the plant when you grow the banana as a fruit. That is 96% waste when you have 1 kilogram of the banana fruit coming in. So it's a huge amount of waste which is out there, which can be utilized. So I tried to show some numbers relevant to that. Again, this is a huge number in thousands of tons. Millions of tons. Biomass to energy pros and cons, and I'm sure a lot of you are already familiar. इसमें बहुत सारे फायदे भी हैं और इसके अपने challenges भी हैं. Obviously, ये renewable energy source है हमारे पास. Carbon dioxide is absorbed when the biomass is growing. So it's a net carbon dioxide absorbing phenomenon or material in the world. दूसरा है कि कार्बन न्यूट्रल है, इसको अगर आप सही तरह से यूज करें तो you don't release more carbon than you can absorb from the atmosphere or from the environment. And obviously, if we can use our local biomass, then we don't need to import fossil fuels from Saudi Arabia, Kuwait, Qatar, and I don't know, Australia and Indonesia. We mostly import the coal from. It can be produced domestically, and sources for biomass energy are easily available. I'm sure you are familiar with a lot of these materials yourself. Low cost in comparison to fossil fuels. Low cost means fossil fuels, obviously you have very high energy density material, but it has huge carbon footprint, but also transportation costs. So it starts from, let's say, from Saudi Arabia somewhere to, I don't know, 200 meters down in the ground, and by the time it reaches to you, it may have, I don't know, $30, $40 per barrel, just transportation and moving costs attached to it. Whereas biomass is a local material, we don't have that. And likewise, it reduces and utilizes the waste, so we obviously helping ourselves rather than generating more waste for our food production, we also use these waste for energy. And on disadvantages side, it's not completely clean. Obviously, when you burn it or use it in some way, you will release some CO2. It's not 100% CO2 free, although it can be carbon neutral. It's economically inefficient in Pakistan at the moment because there is lack of technology both to collect, process, and convert this material into the usable energy or other forms. It can lead to deforestation, especially if you are using wood from forests and other resources. Or obviously there are a few other, and one key drawback with biomass is the low energy density. You have a lot of material and you may have only, for example, if you bring a truckload of material full of rice straw, you might be only bringing, I don't know, 2 megawatt of energy, whereas same amount of coal can give you 6 megawatt of energy. So that's the difference. So kilogram cost per kilometer is very high for the biomass. Okay? So the next thing which is very honest, which comes in mind is how to use this material in a value-added way so that we can extract maximum benefit from it. Obviously, we have lots of this material available, and you might have seen some attempts by the government where they were trying to prevent this rice straw burning during winter time, which causes smog and a lot of other issues. तो इसको कैसे जो है ना हम टैकल करें? तो इसको जो है ना हम इस तरह देखते हैं कि बायोमास किस स्टेट में और कहाँ पे पड़ा हुआ है. State means what is the physical state? How big is it? Do we need to cut it? Do we need to collect it? What is the collection machinery and technology? Who is going to collect it, and where are they going to store it? And where will it be utilized in the end? All these things have some sort of big impact on the value chain of the biomass. So residual biomass is biomass, something which is sitting somewhere. Let's say this is rice straw after rice crop harvest. Material is sitting in the farm or in the field. This is residual biomass. Nobody wants it. The farmer has to get rid of it. There is a bit of, let's say we can attach some number to it, and that is, the number is in pence per kilowatt. Since we've done some research from a UK perspective, so this is in pounds. British pound is about roughly equivalent to 1 pound is equal to 1 pound. So we have about -10 to -5, which means somebody, I mean, it depends who has what, but mostly somebody will have to pay or will have to incur some cost to get rid of this material from that field, or if it is somebody else, like municipal solid waste, somebody needs to pay for this material to get rid of it. So there is an opportunity for another person to actually gain some advantage and do a value addition. So this will be the first step. Second step is pre-treated residual biomass. So at this stage, the material is now collected and perhaps locally stored. So it's not in the field, it's sitting in a shed or in a warehouse or some sort of a vehicle. And this is now still maybe in Pakistan, here it will have some positive value rather than negative value. But you can see it's still kind of at break-even level. You can't make huge profit. But we need to add more value to this material. We have thousands, if not millions of tons of this material. How we can convert this into a currency? How we can make it economically viable? So the next step is we take it to process some fuel products. So this can be, for example, your solid fuel biomass pellets. It can be your briquettes. It can be, for example, wood chipping. If you have wood material which is more sort of branches, you can just chip it and make it easily transportable and movable. That is what we are doing. And now we have a positive value. And this is per kilowatt hour. So each kilowatt hour of that material can give you 2 to 5 pence revenue. Let's take it to the next step and we produce, let's say, we do a process. So we've done some physical processing and now we're looking at more sort of advanced level of engineering. We are doing some thermochemical or chemical or biological treatment. And now we have the end product, maybe it could be heat, it could be biogas, it could be bio-oil, biochar, or something else. And now you can see your value addition is nearly doubled from biomass to products, which were the crude products which you could have used yourselves, but now you have a product which is usable by the downstream industries. And you have done really a big value addition step. And ultimately, if you can produce electricity or some sort of a gas which everybody is using, whether it's industry or residential, you have a commodity which everybody needs. And we all consume energy, a couple of kilowatt per day. And that is the value for money, basically. And this is how we have the value addition. So this is what we all should be aiming for when we look at the waste. This is how we are going to achieve the value addition. So the next step comes into mind, what can we do with this material and how and what kind of technologies we can use to actually process this material. So there are a lot of different technologies people have developed during the last few centuries, let's say. Combustion is old favorite, the caveman favorite. They burned some wood and generated heat. We're still doing that, but we need to do better than that. And that's where we can have value. So we have two types of processes, thermal processes and bio-based or biochemical processes. And you can see, I don't want to elaborate on every single one of them, but you can see what kind of processes can be used, but this will be feedstock specific. What type of biomass you have, how much, where it is, and what is the end product you want. So all these will dictate different treatments and strategies and different business models. So we got biomass, we know how much it is and where it is. Now let's say we need to select a technology which we can use to actually get the final value addition step to have a commodity which we can sell. Obviously, anaerobic digestion it's been there since 60s, 70s. A lot of these systems have been installed. Some were very successful, some were very crude. People treated them just like a cow shed rather than a plant. And this technology didn't succeed in some areas. But it's still a very usable and very big scale technology in Europe. And end product is biogas. And biogas is a natural replacement to sui gas or natural gas which we use in houses for cooking. Next kind of technology which we have is thermal technology, pyrolysis or clarification if you like. They're kind of similar, but there are a little bit of difference between both. They both are done in absence of oxygen. So the biomass, when it's heated, there is no oxygen or air in contact with that biomass. If air was to come in contact with that biomass while it's heated, it will burn. And there is a general rule of thumb: if you have hot biomass above 320 degrees Celsius, whether or not you apply the ignition source, it will burn, providing there is oxygen. It will burn. And obviously it will depend on how pure that biomass is. If it's very cool, it may not burn, and you need to evaluate the temperature. So there is a temperature range which we can use, 300 to 650 degrees Celsius. 300 is more common for clarification, between 200 to 300, and we will go in more detail about clarification and the benefits of it later on. But here is just a little bit of intro about the technology. And the benefit is it can use complex mixture and standalone materials which exist in the agricultural and municipal sector. So the technology is kind of flexible to accept any kind of material. And it can also accept high ash containing, high moisture containing material. And the end product are biochar, biocoal. Biochar and biocoal are the solid products, and there is a key difference between both. Biochar is more than 80% carbon or biocarbon, whereas biocoal, it has a little bit of biovolatiles released from it, but it still has a lot of other hydrocarbons, which is carbon, hydrogen, and sulfur and chlorine, and perhaps also nitrogen. So it's a little bit crude than biochar, but it's a very good material itself as well. Bio-oil is obviously it's a liquid form of the product. It is obviously hydrocarbon based. It has its own challenges and applications. And syngas, which is the gas which is uncondensable. When you pyrolyze something, you produce three things. You produce a solid, which is biochar or biocoal. You produce a liquid if you quench or cool those gaseous vapors, called bio-oil. And there is some uncondensable gas which will be produced, and we normally call it pyrogas, producer gas, or syngas. Each one will have a different meaning based on its calorific value and type of technology used upstream. Next one is gasification, and by the way, in pyrolysis and clarification, the main thing, as I said, is the oxygen. There is no presence of oxygen while the material is heated. There's a little bit more detail and information in next slide, so I will go through it. Gasification. So here we are just looking at the key differences. Gasification is kind of a bit like pyrolysis, but here we introduce some air deliberately, but not enough that we completely burn the gas or the biomass itself, so that the end product is some sort of a gas which is combustible, and that combustible will be used in the final technology where you use it in a genset or generator to make electricity, or you use it in a gas turbine to burn it and produce electricity, or use it for hydrogen production, or you can even use it for making some other biochemicals through synthetic tools. So, and you can also have heating and cooling which you can recover from the combustion of it. Next one is combustion, and this is in fact the first one, because this is the caveman technology. Burning some wood between the stones. And it mostly is done at elevated temperatures, and we have abundance of air and oxygen. And you are burning uncontrollably sometimes. And you are producing end product as a heat, which will be used to produce steam, and steam will drive your turbine to produce electricity. Or you can use just the heat to drive a furnace or some other process. And last but not least is transfer esterification. This is a process where you chemically process a lot of these vegetable oils to produce biodiesel, and we done that lots of time. And end product is very similar to diesel, and it can only be used in diesel engines or diesel burners. Okay? Energy conversion steps. So this is kind of a summary slide of the previous slide. So the end product and what is the intermediary technology between the thermal processing technology and the end product. What do we need? So we need either a gas engine or a turbine or some sort of a combustion system. So the technology type, so here there is a little bit more information. So when we say pyrolysis, and pyrolysis is in absence of oxygen or air, we have temperature range between 300 to 700, and by the way, this is no limitation. You can do pyrolysis even at 800 degrees C if you want. And we have biochar as end product, and we also have a combustible gas. And in here, slow pyrolysis, we have the solid or the biomass residence time within the reactor in the order of minutes or hours. So material sits in the hot zone for a couple of minutes or maybe up to hours, depending on who is designing what. Okay? Fast pyrolysis is also like slow pyrolysis, but the key difference is how much time is spent by the biomass in the reaction zone. Here we are talking seconds, maybe 1 to 3 seconds, and this is done in a very dynamic environment in a fluidized reactor. And gasification is again, it can be a combination of slow and fast pyrolysis, but here we have air or oxygen present, and we have very high temperature, and we can also use a catalyst to aid the decomposition of biomass to hydrocarbons and then enable the use of it. And torrefaction is, as I said, it's similar to fast pyrolysis. It's done between 200 to 300 degrees C. Sometimes some people introduce a little bit of air to burn the vapors within that process itself, but this is not universally true for all systems. Here, the objective is to maximize the biofuel production by losing as little as possible of the calorific value of that material. And you can say in this process, we retain the 80% of the energy content of the material compared to the fresh biomass feedstock. And here also, we completely remove nearly 90+% of the moisture which is within the biomass feedstock when it comes to it. So that's the key difference. We have more slides later on about this process. So now we know a little bit about the technology itself. What about the reactor type? What about the actual system which we will use? How does it work, and how will it look like, and how do we make it work? And what kind of automation and control it will need to enable you that kind of end product which you want to design or do the value addition. Okay? So here we have pyrolysis reactors. In fact, this can also be true for gasification and torrefaction reactors as well, to some extent. We have fluidized bed reactor, and there are two different types. There is circulating and bubbling fluidized bed reactor. I don't want to give you too much complex information, but this is some sort of a system where biomass is fed inside a big vessel, and some sort of an air or fluidizing media is passed at the bottom, and everything kind of bubbles inside because of the pressure difference. And while it's bubbling, and if you were using the air, this will do both the mixing as well as the combustion or gasification or pyrolysis, depending on what you want to do. Likewise, we have fixed bed reactor, Auger reactor is quite popular. We, in fact, are working both on fluidized and auger reactors. We have patented an auger reactor. And then there is another, what we normally call continuous still tank reactor, CSTR. This can also be used for processing something like this. And then rotary kiln reactor. A rotary kiln is where normally they use it for producing activated carbon and for drying a lot of different types of material. And then there is ablative and column types. These are less common, the last two. So some systems which we developed in the past in UK, in Germany, India, I'll give you a little bit of flavor. So the first one which you see on the left hand side, this is a system which we developed for IIT Ropar, which is an Indian Institute of Technology in Punjab. It's near Chandigarh. This system was developed by Aspen University, where I was working, to process rice straw waste, to produce biochar, and also to produce bio-oil, which was blended with the biodiesel or diesel to drive and produce electrical power. The next one is, the first one, sorry, is 20 kilogram per hour, a small scale research reactor. The next one is a big scale of the first one, but it has some other innovations inside, and it's a patented system by the European Bioenergy Research Institute, which we developed and designed and built. And I spent, in fact, I've done half the PhD on this system. So this system is 100 kilogram per hour, and the ultimate objective of this was to process a big variety of biomass and municipal solid waste, to produce biochar and also to produce a bioliquid which is blended with diesel and biodiesel and then used as a liquid fuel for diesel engines. And last but not least, on the right hand side, this is a system, the middle one is called pyroformer. This is a trademark name of the technology. If you Google it, you will know. It's doing pyrolysis and reforming of the gaseous vapors. Last one on the right is called TCR reactor, thermocatalytic reactor. This is what we designed to produce something called biojet fuel, a fuel which was used in aeroplanes as a blending fuel at 10% ratio in Germany, and it was a kind of a tri-national project between Germany, UK, and Netherlands. So we developed this technology. I was chief engineer for designing this system. This was done in 2019. So you heard me saying quite a few times bio-oil. So what is bio-oil actually? So bio-oil is a very complex mixture of different hydrocarbons, mostly in liquid form. And it contains water vapor, which is obviously mostly combustion product, aldehydes, carbohydrates, phenolics, ketones, and other unclassified compounds in minute quantities. And we have given a range of those percentages. It has calorific value, which is, we try to maximize the calorific value to be comparable to diesel, but you can't get very near to it, but it has less than 70% of the properties of the diesel fuel, which is 16 to 30 megajoules per kilogram. The diesel and biodiesel have calorific value in around 42 to 45 megajoules per kilogram. And it has viscosity between 2.5 and 3.4, and in some cases up to 40 to 100 centivolts, which makes it inferior fuel compared to diesel. So you might be thinking, why do we make this fuel when it's inferior? Well, the problem is we don't have technology advanced enough to process it in one step. We can do further processing, but that adds up more cost for processing to produce diesel quality fuel. And we have done that as well in this FlexJet which I was referring to. So this is the bioenergy. So we looked at pyrolysis, and now we look at gasification. And gasification is something which I have been doing for more than 10 years. This is processing of biomass by including air or oxygen at high temperature, mostly at higher than 800 degrees Celsius. And we produce a gas, we call it syngas, it's also called producer gas. And we clean that gas so that there is no air power. And you can also use this gas, by the way, in a fuel cell, in solid oxide fuel cell. I designed and built a system which was used in a fuel cell research center. So the key step is upstream processing. So we have biomass which we need to densify, make it in a usable form so that it can be used as a feedstock in the reactor. Then we do the gasification, and after gasification we have downstream processing, which is gas cleaning and gas conversion to electrical power outcome. I hope it's straightforward. Yeah? So gasification is a thermochemical process that converts carbon-containing materials into combustible gas, which is syngas. And syngas is SYN, which is similar to synthesis gas. And it's a mixture of carbon monoxide, which is CO, CO2, which is carbon dioxide, hydrogen, some nitrogen if you are using air as the gasifying fluid, and obviously there will be water vapor and some other minute compounds such as chlorinated gases, as well as some unburned hydrocarbons, sulfur oxides and nitrogen oxides. In case of biomass feedstock, this gas is known as wood gas or producer gas, which is composed primarily of carbon monoxide and hydrogen as fuels. Carbon monoxide and hydrogen and some methane are the only combustible gases which is present in this gas mixture, which will give you the calorific value. Carbon dioxide and nitrogen and water vapor is undesirable, but it's present in the system because it's coming with the air, and water is coming from the combustion process when carbon is reacting with hydrogen and oxygen. Okay, don't want to make you completely bored on this, so I'll push on. So it's a very simplified diagram what happens with the biomass. If you were to produce a producer gas, and that's an inferior quality syngas, you have biomass to syngas, producer gas process. And if you process at very high temperature at 1200 to 1400 degrees Celsius, or under catalytic gasification conditions, you produce a syngas, which is very high quality gas. It can be used in engines and burners and gas turbines. You can also produce biohydrogen. You can produce natural gas or methane. You can produce a lot of other chemicals like methanol, ethanol, and other synthetic fuels which are normally coming from the fossil fuels or petroleum fuels. So this is again difference between producer gas and syngas. I don't want to complicate too much, and don't want to read the slides out to you. You can see it yourself. But the key difference is the quality of gas. Producer gas will have slightly less calorific value of the gas, whereas the syngas will have higher calorific value, more than 8 megajoules per meter cube of gas. Whereas producer gas will have between 5 to 8 molecules. Combustion system, which is your gas turbine or a gen set. When I say gen set, I mean internal combustion engine, same engine which we use in your car, for example. Or you can have a fuel cell or a heat recovery system where you burn something and then you produce steam, and steam gives you the electrical power. And obviously you have the capability to produce some more complex fuels as well as the chemicals. So I think I elaborated enough on this. So as I was saying, you can use the syngas or producer gas coming from a gasifier in many different ways, including engines, compressors, hydrogen fuel production units, gas turbines, fuel cells, a variety of them, and you can also make a variety of chemicals from it, which are given at the bottom. So we looked at quite a few different types of these technologies. What is really, let's say, coming into mind is, what is the best? What should we really use and why we use it? And obviously, when you say, what is the state of our best system, it will also have some cost attached to it. There is a capital cost attached to it. So we invented a process called pyrogasification, where we kind of separated the pyrolysis and gasification to produce the end product, and also at the same time produce biochar and no biooil, which normally is produced as a product from pyrolysis. But we also produce something called syngas in this case, and this process now allows us to use a big variety of feedstocks. The drawback with gasification on its own is you cannot use complex residues which have irregular shapes, or they have very high ash and moisture content, or they have low ash melting point. When I say ash melting point, it is something which is a property of the material. When you heat it above 600 degrees Celsius, this material, which is like ash from your biomass burning, it starts to melt, and it goes through glass transition temperature, and it becomes more like a paste, like honey. And if you only give it 50-degree temperature difference, it will become solid, and it will cause huge problems in these reactor systems or downstream, where you want to use it into an engine or fuel cell or gas turbine. So the pyrogasification system allows us to use complex materials. And when I say, why do you want to use the complex material? The objective is to get the material which has negative value. You don't pay for it, somebody pays for it to take away that material, and you use it to achieve the maximum value. That's the objective. That's why we want this complex material, and that's why we need this technology. So, and also by doing this processing, we reduce the number of steps required to process the waste to achieve the end benefit, to have the commodity which we can sell. And this system allows us to do that. We also have the ability to enhance the process utilization and energy conversion efficiency. What does it mean? It means that the amount of material you will bring, you can get maximum value out of it. You can get maximum usable end products from it. Whereas through pyrolysis, you have a biooil which is complex. You cannot processing. This is all about process economics. How to maximize the value addition so that you have. So this is another system which we developed and built during my PhD, but also when I was working as a bioenergy manager in Birmingham City, UK. So this is on 4 floors. At the very bottom, we have the ground floor. We have char discharge system, and char is biochar basically. And we have engine and some scrubber system. You see a tank and a few other things and heat exchangers and so on. Then on the other level above, which is the ground level, but in this case is on the number 2. This is a scrubber and a pyroformer, and in fact we have 2 pyroformers which are connected to a system. And the blue thing in the middle, vertical, that is our bubbling fluidized bed gasifier, and it's huge. It's more than 3.5 meter diameter, and we have, because we are running it at more than 1000 degrees Celsius, just to insulate, to prevent the heat loss, we have to use about 1 foot thick insulation bricks inside. So this is the gasifier, and further up is the heat exchanger, cyclone, and so on. And on the very top, which is very top and roof of the building, the orange things, this is the HVAC system for the building to manage the, let's say, good air quality within the building environment. So these are, again, those systems which we installed in the previous slide which you saw the building. At the very bottom, somebody standing with this high-vis jacket. This is the gasifier. You can see the scale of it. The pyroformer, the technology which is 100 kilogram per hour reactor. It's a continuous system. It's on the top left. And on the top right is the research institute. And this building, which you saw in the previous slide, is in the back of this research center. And you can see on the top of the building in the bottom right picture, the front is here, and on the top behind is all those HVAC systems and so on. It was a huge facility basically, and it still is there. So this system was designed to use wood pellets as the biomass feedstock, which we were importing from Scotland into England. But also we found that we have a lot of waste straw available in straw pellets available in England, which we also try to use in the system. So this is the kind of energy distribution system what you see at the moment. So in the middle over there is the engine, which is the MAN energy conversion system. It's a MAN diesel engine. MAN is the company, by the way, MAN. It's a half a megawatt power production system, and we built this facility to be a research facility, but also more like a pilot project to actually test a variety of different biomass feedstocks, but also a variety of different technologies like engines, gas turbines, and heating and cooling systems to be integrated in the system. So we could use about 7 different types of fuel mixes in this engine. So we could use the waste engine oil, biodiesel, diesel, all these with the pyrolysis liquids, with the pyrolysis gas, also with the gasification syngas. So we could use a combination of those in this facility. And this is what we used in my PhD. These boxes on the right-hand side, number 17, each one of them represent a building. The power coming from this engine was going in 4 different buildings. And I'm talking live buildings as we are sitting here, for example. That we were powering these buildings from this engine. And for example, one is every building, then we have this research institute itself, where about 200 people are working. That was running from this facility. Also, we had student union building, which was running from this engine. And another few library and a few other buildings where we were providing heat and cooling. And all this system was also backed off with the gas boiler, so that if we have some problem, and because now we are providing the energy to live building, people are working inside, we cannot just tell them, oh sorry, our engine failed, you can go home. That's a big loss. So we have backup systems. So we have gas-fired boiler, and we also have electricity from the grid. If we have any problem, automatically system switches to the conventional systems. So this is what we installed. And also we installed electric charging and discharging system, first of its kind, and I'm talking 2014 and 15, where electric cars were just, people were starting to talk about it. So we could charge electric cars from biomass, and we can also discharge the stored energy in the batteries to power these buildings again. So for example, our engine is shut down for 5 minutes for some reason. We can use the car battery as a generator to supply the energy back into the building. So this is the pyro-gasification concept I was talking about, a process flow diagram. How does it look like? And you can see that there are quite a few different things which are happening here. We have biomass coming in, and on the left-hand side, then we have gasifier, red box. We also have a pyroformer at the bottom, which is orange box. So both of these can be used in such a way that we can use more refined kind of biomass in the gasifier, but we can use very crude and low cost, in fact negative cost feedstocks in through the pyroformer and take that gas to be gasified. And then further it needs to be cleaned, and heat needs to be recovered to be used in other parts of the process. We also have the rapeseed oil, which is, I'm sure you are familiar with सरसों का तेल जिसको आप बोलते हैं. उसको भी हम यूज कर सकते थे इस स्क्रबिंग सिस्टम में, और उसको भी एज फ्यूल हम इलेक्ट्रॉन इस्तेमाल कर सकते हैं. और ये सारी चीजें जो है फिर वो आगे जा रही हैं क्लीन होके. After 5 micron filter, we take it into an engine system, and that's where we are producing electricity, but also we are recovering twice as much heat, which is now used in the central heating system of the building. So we don't need to burn the gas, for example, and we can recover the heat. And the total energy efficiency of the process was 78%. So what does it mean? 78% of the energy content in the biomass can now be used as end product, either in the form of electricity or heat in the buildings. This is a huge achievement. Your conventional engine system is maximum for 25 to 28, maybe 30% efficient. That means 70% of the energy is wasted as heat. We recovered. So that's the key advantage there. This is the gas composition which we produce. So you can see the things going all over the place. This is the live picture we taken of the gas analyzer system while running the system. What is the temperature is the blue line there. You can see that time stamp, the gaseous composition, and so on. So gaseous composition is changing every second. And we don't have a huge control over it. We have some control, but we cannot control very, very precisely. The only thing we can control is pressure and temperature. We cannot control the composition. That's a characteristic of the material itself. Okay, so all these systems are obviously, when we are installing these, we need to comply with the local regulations. You can't just put up your gasification or pyrolysis system in the middle of nowhere without getting permission from your local authorities. So in our case, these were the regulatory standards we have to follow, and I was ensuring that we were compliant with this. Next thing, and this is again the standards which they use to measure the emissions and composition of the emissions and how often they measure this. So this is again given with all the numbers. Maybe less relevant to you at this stage, but it will be relevant when you start building a project like this. It will be very, very relevant at this stage. One of the key projects which I was involved in and I was referring to, how can we use the sewage waste? Again, it's available in millions of tons quantities. In Europe, they have sewage treatment plants, and they produce millions of tons of this every year. They don't have any good way to use it. In fact, a lot of times they just landfill. So we connected with the sewage treatment works, and they would pelletize this material, and we were using that as a feedstock in our process to make petrol and diesel through this waste biomass. And again, this was a very, very expensive project. I mean, it's not economically viable, but we had achieved the kind of fuel standards which are applicable in Europe. So this is another project, and by the way, you can Google these processes and technologies and projects. To Synfuel and FlexJet project. This was funded by European Union, and I was working on designing this pyrolysis reactor for this. And the objective was to produce sustainable aviation fuel to be blended with the conventional aviation fuel at 10% ratio, because they have a new regulation just came out. In fact, it was in discussion at that time in 2017-18 that by 2025 all aviation flights in Europe will have to have 10% renewable fuel. So this project was to address that future demand, and we've done some work. This is our project which I worked on in India while I was working as plant manager in Aston University, and this was a collaboration between India and the UK government. Here we produced a mobile pyrolysis system which was powered by diesel blended fuel, and you can see a generator in the yellow box. And this was stored in different villages in Punjab, in Indian Punjab, and the objective was to stop burning the rice straw, and I'm sure it's the same problem in Pakistan, which we are facing nowadays as well. And that project was called Energy Harvest. So instead of just harvesting the rice, you're harvesting energy at the same time. This is our most recent project. We are also partnered in this project, my company called Eco Research Limited. This is where we produce banana-derived textile, and also we produce electricity biochar through our biogasification system, so that we can use the biochar as a biofertilizer after upgrading it to certain stages. It can go back to conventional agriculture, but also it can go back to the banana farming industry. And also we recover the energy from the waste after we have produced the textile itself. So there is about 60% of the waste which is produced after extracting the textile from the banana stem itself. And when I mean banana waste, I'm mostly referring to the banana stem, because banana peels cannot be collected in such a quantity to be processed. So this is called a SAFER project, and it's currently running, and we are installing a biogasification system in Sindh, in a city, a small town called Sadiqa, and inshallah from this April to July we will be testing this system. There is a little bit of video, but I don't know if it works, but I'll show you the system. So this is one of the very first reactor systems which we built, and the beauty of this system is to do the pyrolysis process, we need heat energy, and normally heat energy is coming from either electricity through electrical heaters or through burning some sort of gaseous fuel. It can be LPG or natural gas. But here what we've done some innovation and patented that. We reuse some of that gas. so that we don't need to rely on electricity or LPG. We only use it in the initial first 2-3 hours to bring up the temperature, and once the process is able to take the feedstock, then we have the gases which are produced from the system, and we recycle and burn them in such a way that it's still safe to be used, but also completely eliminate or reduce those supporting fuel gases such as LPG and natural. So this is a pyrolysis system, screw pyrolysis or over pyrolysis system, which we built and delivered to Kuwait Institute for Scientific Research in 2018. Last few slides before you get bored, but I'm sure that some of you will be finding it very interesting. So this is the clarification process. As I said, it's kind of similar to pyrolysis. The only key difference is the temperature is quite low. Instead of running the pyrolysis process at 500 or 600 degrees Celsius, here we use about 200 to 300 degrees Celsius temperature. And the objective is to keep maximum weight of the biomass so that we have end product which has very high energy density and very high calorific value. And that's the objective. And the end product here is not going to be used in this process, but this is a kind of a solid fuel which can be used in a lot of other industries, and we will come to that later. And obviously here we kind of reform the system in such a way that we are drying the starting feedstock, we are doing the torrefaction, but also burning the gaseous vapors produced from the torrefaction reactor in a combustion system, and they're both supporting each other. And then we cool the product, which is the solid product biocoal, and biocoal is then pelletized into end product, which looks like this. And it's more brown rather than black. So the samples you were looking earlier in a few minutes ago, you saw the black biochar. This is a different variant of that. It's more brown or kind of half-cooked or roasted material at 200 to 300 degrees Celsius. So given some potential uses of the torrefied pellets, mostly in power generation. So you might think, why we use this in power generation? So think like this. Pakistan is importing a lot of coal from Indonesia and Australia, I think. But also they have huge local production as well. But the quality of that fuel is quite good. So if we can compensate some of this coal with this biocoal, and that biocoal is, for example, coming from Punjab, imagine how much value addition we have done, how much carbon savings we have done, and how much foreign revenue which we were sending in the form of dollars going to Australia and Indonesia can be saved. Likewise, we can use these biocoal as industrial heating solutions in a lot of different industries. I think mostly in textile industry, you use them for generating steam, which is used in dyeing in a lot of the processes. So this can again replace that coal. Residential heating, believe it or not, wood pellets are being used in Europe in households and schools and a lot of these community buildings where they are generating heat for winter to actually run these buildings on a renewable fuel like wood pellets and sand. Biocoal can also be used. And obviously, last but not least, we can also use these biocoal pellets in co-firing in power plants. So these power plants, they exist in hundreds, if not in thousands in Pakistan. And if we can displace, let's say, 10 or 20% of that coal, it's a huge improvement, both in terms of carbon emission savings, but also supporting the local circular economy. Because now the rice straw which was burnt in Punjab has a value, and the farmer has a reason to collect it and there are new jobs which can be created in the whole supply chain. So some key benefits I try to highlight here, and don't want to read every single one of them, but the biggest one is by producing biocoal, we are maximizing the energy density of the material. You might have a question, why do we make biocoal when we can make solid biomass pellets? The answer is that solid biomass pellets will give you low calorific value. It will be very smoky, and it cannot be used as a fuel in the power plants directly where they have to mill the pellets. It's not brittle enough. It's more ductile and fluffy material. Whereas biocoal is very brittle and it can be broken down by the same machinery which is already installed at the power plant. So that's one of the key differences. And obviously, other benefit is that by converting biocoal and maximizing the transportation cost, so that if you are transporting 1 ton of this biocoal compared to the solid biofuel pellets, you have more energy, but also you have more material which can be transported. And it's stable, it will not rot. Biologically, it is more stable. It's also water hydrophobic. It will not absorb the water. So the shelf life of this product is in months. Compared to biomass, it might start to rot. It will catch mold and fungus to actually start decomposing. So you cannot store and transport the biomass as easily compared to biomass. And there are a lot of other things which are highlighted, including removing the moisture. That gives you one key advantage. So normally you are carrying about 15 to 20% moisture as water present in the biomass pellets, whereas in this the moisture can be maximum about 2%. So again, maximizing the energy density. How much energy you are carrying in one truckload from, let's say, Faisalabad to Hyderabad, I don't know. That is the key benefit. So again, some key technologies which I have given here and are given a reference. It's again taken from another European project. We can see that we are retaining about 79% of the mass of the material when we're feeding the biomass into the reactor, and what kind of heating and heating mechanism do we have. Energy yield, so you can see 90% of the energy is retained in the biocoal in the center project there. And net thermal efficiency, so 92% is the thermal efficiency of that plant. So it's very, very cost effective. So we're not pyrolyzing enough so that we liberate a lot of those hydrocarbons, and we try to retain them as much as we can. And then we have the thermal energy consumption per kilogram. So to process 1 kilogram of biomass to produce 1 kilogram of biocoal, that's the amount of energy in kilowatt hour is needed in each different process. So torrefaction technology reactors. So here I've given some of these established systems. These projects are live projects. Somebody already installed these technologies. So there is a rotary kiln reactor, and this is an overreactor. And I have given some more details of which company has installed it, which country has it, so all the way from USA, UK, and Finland, and so on. This is again, I'm sorry you cannot read it, but what I was trying to highlight is the design parameters when you have a small lab scale system and you want to upscale it to, let's say, 10 tons per hour system. You need to take huge amount of information into account to ensure that your system will work, it's robust, and it's economically viable. It's not just an environmental solution, it it has to make profit for the business to sustain and make and install more of these units in the country. Another slide to show a lot of these other torrefaction systems installed around the world. If you Google very precisely, look into literature, you might be able to find this. But I have shown some information there. So, I think we're coming to the second last slide. So, the systems which we talked about are continuous systems. You might have heard about this charcoal which we normally make, and it's available as a barbecue charcoal, using it in various different industries. That's a completely different product. It's made in a completely different way. It has huge labor costs attached to it. It has very high carbon footprint attached to it. And why this carbon footprint is attached to it? Because when you are producing this charcoal, you have about 70 to 80% of the mass of that biomass going in the gaseous form, and they are emitting it into the air. Sometimes they burn it, and most of the time it's not burned, and it's dark black smoke. And that is the carbon dioxide and a lot of other unburned hydrocarbons which are released into the environment. By having those technologies which we just discussed, we are preventing all that gaseous emissions, but also at the same time we are not burning the fossil fuels to generate the same amount of energy which was to come from combustion of gas or coal. So we are also saving on that. And if you are going to work on this system, there are huge number of challenges. A lot of teething issues, what we call them. Something will go wrong. It's not that it's a complete failure. It's just that during technology development, you have to address hundreds of different problems. Some could be technical, some could be more economical, and some could be with splash energy. And the most optimum way is to have an integrated energy system where you can maximize the energy conversion, and you also use that energy either on site in your own system, or you export it as hot water into district heating network. Some new term for you. In Europe, they have district heating network where hot water is supplied from one facility, same like our water is coming in our city from one place. They also have normal tap water, but also hot water which goes through heat exchanger in each house. So by integrating these technologies, we can maximize energy conversion, and we can save on conversion of coal and gas to generate that. And state-of-the-art system which we are working upon, a biogas system, is still in development, and inshallah we've done most of the fabrication in Pakistan. It's designed in UK, built in Pakistan, first time ever. And inshallah in next 2 to 3 months this should be working in Syria. And we also are in discussion with Daniel who may be using some of it in India. And that's about it. And I'm really sorry if I made you bored, but I think this is very good information for some of you who have interest in bioenergy. So, any questions?
डॉक्टर जैसे कि हम सब ने डिस्कस किया, इन द इंटरेस्ट ऑफ अंडरस्टैंडिंग मैं उर्दू में आपसे ज़रा सवाल करूँगा ताकि इस सब्जेक्ट को ज़रा बेहतर तरीके से समझ सकें। तो बायोमास की अगर बात करें तो इस वक्त पाकिस्तान में बायोमास की यूटिलाइजेशन तो इंडस्ट्री में काफ़ी होगी। तो अगर फैसलाबाद की चले जाएँ, हर इंडस्ट्री में जहाँ पे स्टीम प्रोड्यूस की जा रही है वहाँ पे ज़्यादातर लोग बायोमास परचेज कर रहे हैं, और एक वैल्यू चेन डेवलप हो चुकी है पाकिस्तान में कि लोग जो हैं, देयर आर कंपनीज, देयर आर इंटरमीडिएटरीज जो कि खेतों में से डिफरेंट बायोमास को इकट्ठा करके उसको जैसे कहते हैं ना बेल्स बना के उसको हम लेकर यूज़ कर रहे हैं। तो व्हाट इज हैपनिंग इज के मेजॉरिटी इंडस्ट्री ने टिपिकल बायोमास बॉयलर्स लगाए, جس میں جو ہے آپ کی کلین جو ہے وہ سیپریٹ ہے, اسٹیم پروڈکشن سیپریٹ ہے, تو وہاں پہ تو آپ بایو ماس لا کے ویسے ہی چلا سکتے ہیں. تو وائی وڈ یو گو تھرو آل دس پروسیس کہ یہ تو ایگزسٹنگ ہے کہ ہم پہلے ایک پلانٹ لگائیں, اس پہ ہم یا ٹورفیکشن کریں اور اسے بایو کول بنائیں یا کریں. تو ان یور اوپینین کہ ایک انڈسٹری جو سمپل بایو ماس یوز کر رہی ہے فار اپ لے مین, اس ساری ٹیکنالوجی کو یوز کرنے کا ایڈوانٹیج اس کو کیا ہے؟
اس میں دو چیزیں ہیں. ایک ہے کہ بہت ساری انڈسٹریز میں انویسٹمنٹ آلریڈی ہو چکی ہے. بایو ماس بوائلر بھی لگ چکا ہے یا کول فائرڈ بوائلر بھی لگ چکا ہے. ان کے پاس انرجی یوز کرنے کی بھی ڈیمانڈ ہے, لیکن ان کی کاسٹ آف پروڈکشن بہت ہائی ہے. ان کو کوئلہ لے کے آنا پڑ رہا ہے یا بایو ماس یوز کر رہے ہیں, تو ان کے پاس کم چوائسز ہے. وہ وہی بایو ماس یوز کریں گے جو لوکلی اویلیبل ہے. تو دے ہیو ویری لمیٹڈ چوائسز. لیکن دیز آر ویری لارج اسکیل اور میڈیم ٹو لارج اسکیل انڈسٹریز. اب ان کو تو بیسیکلی اپنے پلانٹ کو اگلے 10-15 یا 20 سال جو بھی اس کی آپریشن لائف رہتی ہے اس کو چلانے کے لیے کوئی بھی چیز چاہیے, اس میں یہ آپشن یوز کرتے ہیں. اب جو باقی کے ہیں لیٹس سپوز کے یہ تو ہو گئے بڑے انڈسٹریلسٹ یا میڈیم اسکیل انڈسٹریلسٹ. دیر از ہیوج اماؤنٹ آف بایو ماس اینڈ ایز وی سیڈ کہ یہ سارا اسکیٹرڈ ہے, ایک جگہ پہ اویلیبل نہیں. فیصل آباد کے لیے چلیں یہ کچھ آپشن ہو سکتے ہیں, گجرانوالہ ہے, گجرات ہے, لاٹ آف ادر ایریاز ان سندھ. ان کے لیے یہ ہے کہ یہ اسمال اسکیل سسٹم رکھیں اور چاہے تو ہم بایو کول بنائیں یا بایو چار بایو انرجی دونوں بنائیں. اور اس میں ایک چیز جو ابھی میں نے زیادہ ڈسکس نہیں کی وہ تھی کہ کاربن کریڈٹس کو جب ہم انیبل کریں گے, اور کاربن کریڈٹس کے لیے یہ ضروری نہیں ہے کہ کاربن کریڈٹس کی کوئی اتھارٹی پاکستان میں ہو, حالانکہ اس کی بھی ضرورت ہے, لیکن وی آر ناٹ لمیٹنگ آرسیلوز بائی دس. وہ اس لیے کہ آپ کی کاربن کریڈٹ ویریفیکیشن یورپ سے ہو جائے. آپ یورپین ویریفیکیشن لے لیں اور اکریڈیٹیشن کروا لیں تو آپ کی ٹیکنالوجی کی پیمنٹ جو ہے کاربن کریڈٹس کی وہ یورپ سے آ کے آپ پروجیکٹ یہاں پہ چلا رہے ہیں. اور وہ اسمال اسکیل سسٹم پھر ہر کوئی اسمال اسکیل انڈسٹریلسٹ یا میونسپل اسکیل یا ٹاؤن اور سٹی لیول پہ ہر کوئی پھر افورڈ کر سکتا ہے.
اچھا, میرا سوال اس طرح تھا سر, میں آپ کا آنسر کرتا ہوں آپ کے کوشچن کا. ہم ڈاکٹر مشرف فرام انرجی ڈپارٹمنٹ. سر ہمارا نا جو ایکسپیریمنٹل فیلڈ ہے وہ ڈفرینٹ ہے. جو بایو گیس گیسیفائر ہے نا, ان کی یوٹیلائزیشن ڈپینڈ کرتی ہے ان کی موڈ آف اپلیکیشن کے اوپر. لائک آپ فوڈ انڈسٹری میں ڈائریکٹ برننگ نہیں یوز کر سکتے ہیں, تو آپ اگر اپنے بایو گیس کو یوٹیلائز کریں گے فار دا پروڈکشن آف سیم گیس دین یو کین یوٹیلائز یور گیس پلانٹ. لیکن آپ بوائلرز میں چلے جائیں, آپ ڈائریکٹ فیڈنگ کر سکتے ہیں. اب ادھر ایک اور کوشچن ریز ہوتا ہے, ادھر یو آر یوزنگ بایو گیس اور ادھر یو آر یوزنگ ووڈ. آپ ایگریکلچر بایو گیس کو نہیں یوز کر سکتے بفور میکنگ آپ اس کو جب تک اس کو پیلٹس میں کنورٹ کرنا ہے, کیونکہ وہ لوز فیول میں ہوگا اس کی وہ انرجی ویلیوز نہیں اٹین ہوتی ہیں جو ایک آپ کے پاس ہارڈ سائز لانگ سائز کے فیول میں ہوتے ہیں. تو یہ ریزنس ہیں موڈ آف اپلیکیشنز بھی ڈسکرائب کرتی ہیں آپ کی یوٹیلائزیشن. بالکل رائٹ. میں اسی تھاٹ کو آگے لے کے جاتا ہوں تاکہ وی کین ہیو اے گڈ ٹیک اوے فرام دس ڈسکشن. دیکھیں, اینگرو نے آج سے کچھ عرصہ پہلے اینگرو کا فوڈ بزنس بھی ہے جس میں ہم لوگ پرائمریلی ملک سے ریلیٹڈ انڈسٹری میں. تو اس پلانٹ کے اوپر جو اسٹیم جنریشن ہے وہ اس وقت ہم بایو ماس سے کرتے ہیں. سو ان اے پرٹیکولر ایپلیکیشن اٹس بیسکلی بینگ یوزڈ ٹو رن دا بوائلر. تو بوائلر سے ہم ایک اسٹیم جنریٹ کر رہے ہیں اور اس میں جو بایو ماس یوز کیا جا رہا ہے دیٹ از سمپل رائس اسٹرا. اس میں رائس اسٹرا بیلز ہیں, رائس اسٹرا کے علاوہ جو آپ کا شوگر کین ٹریش ہے وہ بھی ہے, اور وہ کام آپ باقی انڈسٹری بھی آہستہ آہستہ ٹیک اپ کر رہی ہے. سو بایو ماس ان وداؤٹ اینی پروسیسنگ ان اے ویری بیسک فارم ہم لے کے آتے ہیں اور اس کو ہم بھرتے ہیں. تو سوال یہ تھا کہ یہ ٹیکنالوجی لیولز یہ تو اپنی جگہ پہ, کیا فرام اے لوکل کانسیپٹ یعنی کہ لوکل پرسپیکٹو میں اگر ہم اس بایو ماس کو پروسیس کر کے پروفیکشن کریں جو بھی کریں اور ہم ایک فیول انہانس انرجی ڈینسٹی فیول بناتے ہیں, آپ بایو فول کی بات کرتے ہیں, تو اس کے بینیفٹ ان ٹرمز آف دا انکریمنٹل کاسٹ آف میکنگ اٹ اینڈ دین دا آؤٹ پٹ دیٹ از کمنگ آؤٹ آف اٹ, ڈز اٹ میک سینس؟ دیٹس ون کوسچن. اسی سے ریلیٹڈ دوسرا سوال یہ ہے کہ آپ نے ذکر کیا چھوٹے پلانٹس تو آلریڈی لگے ہیں, تو دیر از اے بگ آئی وڈ سے لو ہینگنگ فروٹ ان دا لوکل پاکستانی انڈسٹری کہ آپ ان کو الٹرنیٹیو فیول دے دیں بجائے اس کے کہ وہ صرف اور صرف جو کہتے ہیں نا رائس اسٹرا کی گانٹھیں لا کے جلانا شروع کریں جو کہ ابھی کی جا رہی ہے. وہ ایک پروسیس فیول نہیں ہے تو اس کا کوئی بزنس کیس یا کچھ بچہ بیس آن ایکسپیرینس ان انڈیا اینڈ آل دیٹ.
بالکل دونوں طرح پاسبل ہے کہ یہاں پہ اصل میں اگر ایک دوسرے پرسپیکٹو سے آپ دیکھیں کہ گیسیفیکیشن پلانٹس اتنے کیوں نہیں لگے یا نہیں لگ سکتے, اس کی ایک ریزن یہ بھی ہے کہ ہمارے پاس اپنی لوکل کوئی ٹیکنالوجی ہی نہیں یا اس طرح کی ہم ڈیولپ ہی نہیں کر سکے جو. اور میں اس پرسپیکٹو سے بات کر رہا ہوں کہ آپ نے صرف ہیٹ نہیں یوز کرنی ہے, آپ نے پاور بھی یوز کرنی ہے اسی انڈسٹری میں, چاہے آپ کا فوڈ بزنس ہے یا کوئی اور بزنس ہے, یو ول یوز بوتھ ہیٹ اینڈ پاور. اگر آپ بایو ماس بوائلر لگائے ہوئے ہیں تو آپ کو ہیٹ تو ملے گی لیکن پاور کے لیے آپ کو ادارہ سے مشینری لگانی پڑے گی. تو بائی گوئنگ تھرو دس روٹ یو آر ڈوئنگ ایوری تھنگ ان فیو اسٹیپس ود سم واٹ لمیٹڈ انویسٹمنٹ. آپ کو اسٹیم جنریٹ کرنے کے لیے اور اس سے آگے پاور کنورژن کے لیے وہ ہیوی اور ایکسپینسو اکوپمنٹ نہیں چاہیے. یہاں پہ آپ صرف ایک پروسیس میں پائرو گیسیفیکیشن فار ایگزامپل کر رہے ہیں, اس کے بعد گیس کلیننگ اور سیدھا پھر آپ انجن یہاں پہ بے شمار آپ کرا کے دی جاتے ہیں. یو ڈونٹ نیڈ ٹو امپورٹ thermochemical conversion technology production in plants.
Moving forward, یہ ساری ریسرچ بیس کالج کافی ایکسپینسو ہے. I was just doing some research and found out کہ یہ ابھی یورپ میں اور یو ایس میں جس لیول پہ ریسرچ کی جا رہی ہے ان کا ڈرائیور کلائمیٹ اور باقی چیزیں. فار کنٹری لائک پاکستان جیسے آپ نے بات کی کہ لوکل انڈیجنس پروڈکشن آف ایسیفائز, اگر ہم اس کو دیکھا جائے ڈو یو فورسی سم وے ڈاؤن دا روڈ کہ ہمارے پاس بایو شارٹ ٹرم اس کا کوئی سولوشن لا سکتے؟
بالکل, اور ہم تو اس پہ کام کر رہے ہیں ایسا سر کہ ہم
انرجی ڈپارٹمنٹ آلریڈی اس کے اوپر ورک کر چکا ہے. ہم نے گیسیفائرز بنا لی ہیں نا ہمارے ورکشاپ میں پڑے بھی.
تو اس کی دیکھیں اس کی اڈاپشن بھی نہیں. دیکھنے کی بات یہ ہوتی ہے کہ ریسرچ میں ہم کافی کام کرتے ہیں,
لمیٹیشن آ جاتے ہیں سر. جیسے نا انڈسٹری کو نا ابھی اعتبار بھی نہیں تھوڑا سا کہ لاسٹ ٹائم میں نے سونیکس وزٹ کیا. سونیکس والوں نے امپورٹ کیا 100 کلو واٹ کا مور دین لائک آپ کہہ رہے ہیں 1 کروڑ سے اوپر کی اسپیڈ کاسٹ اور وہ 100 کلو واٹ کا تھا. ہم نے 25 کلو واٹ کا بنایا ہم 22 لیکس کا. ٹھیک ہے, تو فرسٹ ٹائم بنایا تھا تو ہمارے پاس بھی ریسورسز تھوڑے لمیٹڈ. انڈسٹری کو بھی اس چیز میں اگر وہ ڈیمانڈ کریں نا گیسیفائرس کو اڈاپٹ کرنے کی ٹیکنالوجی تو انہیں ہمیں بھی تھوڑا سا ساتھ لے کے چلنا چاہیے. تو اب ہم نے یا تو گورنمنٹ سے چیزیں اڈاپٹ کرنی ہوتی ہیں یا پھر سیلف ہوتی ہے. اب ہم نے 2 ملٹیپلائی کیے ہیں, ادھر کیا گیرٹ کو بنا کے دیا اور ایون نسٹ کو بھی ہم نے بنا کے دیا ہماری ٹیکنالوجی میں. تو یہ تو اکارڈنگ ٹو دا نیڈز ہے کہ آپ کس چیز کی نیڈ کرتے ہیں. اب پائرولائزر بھی ہمارے میں ڈیولپ کر لیا. تو اب پاکستان کے اندر جو ربر کی پائرولائزر ہے وہ بین ہے. کیوں بین ہے؟ اس کی ریزن ہے کہ ہم ہاف ٹیکنالوجی کو اڈاپٹ کرتے ہیں. اس کو فل ٹیکنالوجی کو اڈاپٹ کریں, پوری دنیا یوز کر رہی ہے. آپ کا جو ٹائر ہے وہ یہاں سے باہر جا رہا ہے, پھر آپ وہاں سے منگواتے ہیں. کول پہ چلے جائیں, سب سے اچھا جو کول ہے پاکستان کا وہ دبئی کا ہے. وہ یہاں سے نکل کے باہر چائنا جا رہا ہے اور چائنا میں وہ پیوریفائی ہو رہا ہے اور دین پاکستان آ رہا ہے. اس کی کاسٹ بڑھ رہی ہے. تو وہ یہ چیزیں ہیں کہ ہمیں کچھ چیزیں اپنے اڈاپٹیشن پہ ادھر اپنے لگانی پڑیں گی انڈسٹری کے ساتھ میچ کرنے ان ٹیکنالوجیز کو ایک پہ نارملائز کرنے کے.
اور اس میں جو میجر بیریئر ہے نا, فار ایگزامپل انہوں نے اچھا کام کیا ہے. تو میرے خیال میں خود 12 سال میں اکیڈیمیا میں نے کام کیا اور آج بس ون آف دا کی پوزیشنز ٹیکنالوجی ریسرچ اینڈ ڈیولپمنٹ مینیجر ون آف دا یونیورسٹی. تو وہاں پہ پرابلم یہ ہے کہ وہ اس طرح کی مارکیٹنگ اور کمرشل اپروچ ہی نہیں ہے یونیورسٹی ایون ان یو کے. اور ایک اسٹینڈ الون کمپنی بہتر کام کر سکتی ہے اس ٹیکنالوجی کو لے کے آنے میں, اس کی کاسٹ کو مینیج کرنے میں اور اس کو ایز اے بزنس کیس پریزنٹ کرنے میں. یونیورسٹیز میں انٹرسٹ تو بہت ہے کرنے کے لیے, لیکن وہ ٹو برج دیٹ گیپ اینڈ ٹو میک اٹ انٹو اے وائبل بزنس کیس آئی تھنک دیٹس ویئر وی آر ایٹ. تو بہت اچھا کام انہوں نے کیا بھی ہوگا اور کر بھی رہے ہوں گے, لیکن وہی چیز ہے کہ اس کو کمرشلائز کرنے میں وہ ایشوز ہیں.
جو گیسیفائر جتنے اسمال کوانٹٹی میں ہوگی اتنے بینیفیشیل ہوتے ہیں. یہ شاید ڈاکٹر صاحب آپ کو زیادہ اس کو گائڈ کرتے ہیں کہ ان کا جتنا سائز چھوٹا ہوگا یہ اتنا ہی ایفیشینٹ ہوتے ہیں.
Thank you.
Thank you. Any further questions from others? جی
सिग्नल नहीं है।
सर जैसा कि अभी बाईचार पे ऊपर बात हुई थी, तो हम जो है जो वेस्ट ऑर्गेनिक वेस्ट है उसको एट अ हाई टेम्परेचर 400 प्लस 300 प्लस के डिग्री सेल्सियस पे इसको बर्न कर रहे हैं, तो उसके अंदर जो बेनिफिशियल चीज़ जो माइक्रोब्स वगैरह है, न्यूट्रिएंट्स वगैरह हैं उसके अंदर जो है वेस्ट के अंदर वो तो बर्न हो जाएंगे, फिर वो हमारे लिए बेनिफिशियल कैसे हो बायोचार?
Good question. First of all, we are not burning it. In pyrolysis, we are thermochemically transforming that material to an end product. Microbes will be lost, that's true. But not all the micronutrients are lost. Most of the micronutrients are retained into the biochar. And we've done, and not us, I mean, there is a whole list of literatures out there where you can look at the micronutrient presence and let's say concentration of micronutrients in biochar. And not just that, you can also upgrade the biochar. Biochar is, think of it like a magnet, like a sponge. Yeah? It has the capacity and surface area within itself to allow the microbial intake into its porous structure, but also to lock a lot of other micronutrients which within its porous structure, which will otherwise will be lost and leached out into the soil, or they will sink into the bottom of the soil. So yes, the microbes will be lost, but this is not all end of the story. We can bring those microbial benefits back into it by doing secondary treatment.
Another question, sir. At this high temperature, it also disturb our environment. So there are no another way. First we treat with some microbes of fungi, bacteria, or actinomycetes. We treat the waste, and then after this process, it will decompose, and then we
Good question. All biomass, if you leave it out there, it will decompose. You will have some end product. If you make compost, you will do some decomposition. And while you are decomposing it, it will release a lot of CO2 and methane emissions, and a lot of other sulfur and nitrogen emissions. And if you are thinking that by doing this high temperature treatment, we are doing more damage, that's wrong. We are not doing more damage. We are in fact saving all these carbon emissions, and we are also displacing fossil fuels to produce the same amount of energy. And obviously we have the logical processes, for example, fermentation and anaerobic digestion, where we are doing this kind of treatment. They have their own benefits and limitations and challenges. But it's not that just because we are processing the material at high temperature, we are going to release more CO2. CO2 is the carbon dioxide which was absorbed by the plant during its growth cycle through photosynthesis route, and it's the same CO2 which we are releasing back into the atmosphere. We are not digging any more new CO2 from the bottom of the ground. That's the key difference. We are only recycling the CO2. We are making a new carbon cycle, so the CO2 is absorbed by the plants, and we use those plants or whatever waste or biomass it is, and it's going back into itself. And one thing which I haven't talked about is the biochar. If you put the biochar back into the soil, there are thousands of studies. If you put 1 ton of biochar back into the soil, you are putting in 3.6 ton of CO2 if you were to burn that biomass and let it decompose naturally. So in fact, by putting 1 ton of biochar back into the soil, you are saving 3.6 tons of CO2. So it's a carbon negative system in fact. Okay. Any more? Okay. Students के लिए तो there are always lots of opportunities. I mean, UK में भी है, यूरोप में भी है, बल्कि यूरोप में तो बहुत ज़्यादा है. तो एक तो यहाँ पे आप अपने तौर पे और स्पेशली जो जिन लोगों की कोई अपनी ज़मीनें हैं या कोई इस तरह की इंटरफेस है, वहाँ पे आप इस तरह के एंटरप्रेन्योरियल सेटअप्स बना सकते हैं। जरूरी नहीं है कि आपको बहुत ही एडवांस किस्म का जिसमें आपको मिलियंस चाहिए वो सिस्टम लगाएं। यू कैन स्टार्ट फ्रॉम something more basic and build yourself. But also there are lots of opportunities to do more academic research into bioenergy and biofuels and renewable energy in UK, in Europe. Always, I mean, just a little bit of advice if you are interested to go abroad, and especially UK, there is a web portal called jobs.ac.uk, and all sorts of jobs and research related opportunities are available. So explore that yourself. Okay, thank you.
Thank you so much. Before moving forward, I would like to welcome our chief guest, Professor Dr. Muhammad Zahir Ahmed Zahir from Institute of Soil and Environmental Sciences, and Professor Dr. Muhammad Naveed. Welcome both of you. Now, I would like to invite our second resource person for today's session, Dr. Fahad Rasool from Department of Agronomy. Please sir, come on the stage and share insights related to this topic.
गूगल पे कहीं कितने आ रहे हो
और फ्रंट कैमरा करके हाया कर उनको बोलो दोस्तों क्या कर रहे हैं देख रहे हो देख रहे हो
मैं फिलहाल अब ज़ीरो इस पहले वाले पे
लेकिन है
पहले 5-6 थे
जब ज्वाइन करते हैं फ्रंट कैमरा करके हाय
For inviting me to talk in addition to this very important topic, converting biomass to energy. And my topic today is about the use of end product of this, or in some cases, the byproduct of that is biochar. Back in 2014, we had an international workshop on biochar here that was by the British Council, and we first time met with Dr. Singh. We explored him through the good connection from the University of Edinburgh, our friend Simon Shackley. And thank you very much, Dr. Singh, for coming again after 11 years. And last year, you showed me in the Ashton University that plant that you have. So I have seen these plants physically. You showed me in Ashton University. Where he was working, where he did that PhD work. And we are more interested in, because this is definitely a big problem in Pakistan, that we are facing smoke. That is the 5th season of Pakistan. For this smoke, definitely, which is coming directly to our nostrils, and that is reducing on average the life of people in Lahore up to 7 years is the increase in the life expectancy due to that smoke. So it's becoming a problem in human health. To avoid this problem and further, because being agrarian and our economy is dependent on that, so we want to fix that problem and use that in another way, that we don't lose this precious resource which people are valuing. Despite the article Act 144 imposed, the farmer lacks technology that what they can do with the rice crop. And energy crisis is also looming. Despite being nuclear power, we are not able to use the civil nuclear technology. So alternate energy is coming from biomass, that is a big resource, and various issues as discussed in the recently in this FAQs. So biochar is becoming an important topic, and a lot of papers, a lot of research has been done. If you just write biochar, huge number of investigations have been done on this precious material, and it has become a very important carbon credit source. And the price of the carbon credit of biochar is among the top credits, which are, and most quality credits are generated through the biochar. If we talk about renewable energy, the carbon credit price is on average $1. And many other technologies are there, but if we use the biochar, the carbon credit price of that is around more than $300 for one credit. So it's the most precious carbon credit that we need to work on, and this is a virtual money. As Dr. Sagi said, so virtual money is lying here, but we are not capturing. It's just like carbon is around us and we are not capturing that. These dollars are in our surrounding and we are not capturing that. So by using this technology and using the biochar, we can make it beneficial for our farmers as well. Recently, an effort was done to study the system. They tried to connect people and make a joint case for the carbon credits. So we can go for a joint application rather than going for individual. So like the similar way we can do with the clustering of the farmers, and they can jointly apply for that. Carbon Canada is the company that is dealing with the southern ecosystem, and they are jointly applying for the carbon credit system. So I will, for the learning of students, I will be quickly telling them that what biochar can do for them. Why we say this is an elegant solution for very complex problems related to the soils and for the environment. So I will be going quickly through this contents because the break time is near. So biochar introduction, and biochar is being taught here from 7 years. Dr. is teaching an important course in the Institute of Soil Environment. The name is Biochar Concept and Applications. So this is a very important topic, and all those master students, they can take up this course in detail, and practically things are being done here. So the background is very clear. We have gone through this. So biochar, as you know, is the product of the pyrolysis, and along with bio-oil, this is the solid content. So this is the solid content. That's why the graduate value is more. People can see visible that they are putting the carbon into the soil. So that can be easily verified. So verification is very important step in this carbon credit. So this is the most important thing that we can put this into the soil. This charcoal type material can be used for energy, but that is not efficient, as we have seen recently from the facts and figures. So the charcoal should not be used mainly for burning. We have alternate sources, and we can use it in different ways. But in this case, like biochar, what it is going to do with the soil, what it can do with the purification of water, what it can do with the various agricultural uses. There are tons of millions of uses now studied in the agriculture sector. It is even recently we have tested that for the poultry feed as well. About 3% of biochar have been used in the poultry feed, and there are some good results, and it is a good churning system for the monogastric type of stomach system. It is even beneficial for that. In Europe as well, there are studies that it is used in the feed of animals for their digestive improvements. So it's not only for crops, for soil, for water, it is also part of the feed system as well. So urban waste, paper waste, aquatic biomass, these can be processed they can be used as a feedstock. So multiple feedstocks and a huge tonnage of this biomass is available as feedstock in Pakistan. The preparation, if we talk about, I'm showing you very primitive type of the system that is still being practiced here. The kiln type system, the traditional heat method, the way we produce charcoal. So these type of kilns are practically in use. And then there are different other old or traditional type of things like this kind of drum system. So pyrolysis, this has been talked about very thoroughly, slow pyrolysis, fast pyrolysis, how this pyrolysis mechanism goes on, and these are the similar kind of elaborations, the mechanisms, how this is converted into different components. So what happens with these production processes, as the temperature increases, there are various processes of the chemical composition also varies in the temperature variable process. There are various processes by which biochar can be produced. There was a very good question that we should use that in a value addition system. And earlier in our previous workshop, we discussed that we can use this biomass firstly for producing mushrooms, and after getting some nutrients out of that, then finally we can go for the pyrolysis process. But that is so to put the things in the cyclic process, we extract some nutrients or the micronutrients that are being wasted from that. So because for mushrooms we need this kind of substrate, waste particle is very important for this kind of working. So the properties, the physical properties are very important, and chemical as well, they are very important, and how it functions, how it acts as a leaching barrier into the soil, how it acts as sponge, how it can enhance the efficiency of the fertilizer, how it can enhance the nutrient use efficiency, how it can improve the water use efficiency. So these all processes, for that we need to do some modifications in that. There are various questions about the pH of the material, there are various questions about how it functions, how it needs to be applied, should it be applied once in a year, should it be applied like a fertilizer. So there are various questions being discussed about this, and we need to talk about all these matters, whatever is we will be talking about that in question answering session. So this is mainly like how the biochar is produced and what type of characteristics are there, and how by understanding these characteristics like XRD, how these biochar can function, because different feedstock biochar functions differently. It is not a homogeneous material. It is usually having the heterogeneous type of nature, and if you cannot get the same result with the same wood, you cannot get the same result with the same type of price. So as the feedstock varies, in a similar way, the properties varies. Likewise, if you produce at a different temperature with the same feedstock, the properties vary. Right? So there is huge variations which need to be documented, and that's why the characterization of biochar, the composition, how the carbon atoms are. So carbon is very interesting thing that diamond is made of what? Can anyone know? It's also carbon. So where we stand, we are using this carbon, the diamond is also carbon, so this carbon is very precious. Depending on what form of that is available and how we are using that. So this is again the characterization of biochar. Various types of spectroscopies are involved, and then we use the microsections. This is how it looks in the microscope, under the microscope. These are the cells, just like the cell walls of the plants. So the cell walls are remaining in the part, and inside content is almost empty. And these are the chambers, and these are the houses for microbes, which can, it is like their homes for the microbes. This place can serve as a sponge. This can save water in case of drought. This can save nutrient and help in avoiding the leakage from the nutrient that we applied. It avoids to go into the deeper layers away from the root zone. So that's why we are promoting it from more than a decade that this should be used, this should be part of the soil, this should be, and we are promoting this in many, even we started with the very crude technologies. This drum system that at least the farmer should be adding some more carbon. So the health of carbon at this point, whenever we talk about the health of the soil, it is dependent on how much carbon is there. Soil organic carbon. This is the organic carbon, which is the symbol of the health of soil. So the issue of pH is not a big issue. It can be modified. We can produce the basic type of biochar. We can also produce the alkaline type of biochar. So whatever type of biochar you need, we can produce that, and we can characterize that. If you need pH, acidic pH biochar, this can also be produced. There are technologies, we can integrate those technologies and make the acidic type of biochar. So especially for in the context of agro, which is a major player in the fertilizer sector, in China about 20% of biochar is placed in the fertilizers. About 20% is a huge amount. So we can learn from those technologies that what China is doing, and practically they are finding it very efficient. This has improved the fertilizer use efficiency of the fertilizers which are sold in China. And various environmental purposes and economic purposes are evident, and its various benefits have been elaborated in the literature. The soil amendments are there, impacts on nutrient availability. These have been thoroughly studied out. It's available in lecture, in literature. Soil microbiology and enzymes, as I talked about, this nutrients and enzymes activity is improved, as I gave the example of poultry. So the poultry is the second largest industry of ours, second largest industry. And if that feed can utilize this part, we have studied up to 3%. It can simply divide in the annual feed, especially the poultry feed. So there is huge use of this biochar. But we cannot feed with such kind of biochar which is produced from the municipal sludge. So that cannot be feed. So for that we need different type of biochar. So depending on the use, we need to have different type of biochar where we are going to deploy that. So we should not be adding more heavy metals into the system. So that is also important. But recently nanotechnology is getting very popularity, and nanomaterials, if you see which type of nanomaterials, they all are coming with the heavy metals. They are either particles with any kind of heavy metal. So we are adding in small quantity, but over the time the incremental effect of that will increase. So how does biochar function? How does it, the heavy metal contaminated soils can be purified? As I mentioned, it acts as a sponge. So this sponge can attach with that these heavy metals, and then it don't make it available for the plants to uptake, and we can safely deploy that. Recently we are studying that in depth, because in Faisalabad we have recently, currently is going on the UKRE project that is led by the Erlang Institute in UK, University of East Anglia, along with Warwick University. So basically they are studying about the gastroenteritis, but one of the pathway of that, which is from the agricultural side, that we are using vegetables grown on wastewater. So on that wastewater, the vegetables grown are not safe. Those pathogens are even in the juice. If you extract the juice of tomatoes, if you extract the juice of lettuce and cucumber, or especially those salad type of vegetables which we don't cook and we are eating that directly. So in the juice of that we have found pathogens as well as heavy metals contaminated with that in the surrounding. And in the reservoir surrounding, about 99% of spinach is contaminated. So to avoid that, we are testing this, that if this wastewater can be treated with biochar, and we have found very good results of that. We are going to publish it so that wastewater grown vegetables, if there is some intervention of the biochar, then we can reduce the load of pathogens as well as the load of heavy metals. So economic purposes have been discussed, like the carbon credit that we discussed at the start. So there are various ways to depict these and various cycles that how the things work, how it can be put into circular economy. That is now the talk of town, that we have to put everything into the circular system. Everything should be recyclable. So this biochar, in this industry, the energy industry, we are attached to them because we are supplying them feedstock, and then their end product, biochar, we are again supplying to the soil. So it's putting that into the circular system so it can work in a circular way. So this is the way their agronomy analyst call, you might remember the 9th call. And then we applied component. There was a question raised from the other side that what is the relation of agronomy with the energy catalyst call? So this I need to elaborate them that this is the linkage. We need to write them that this is the linkage where feedstock is used for the bioenergy, where we are using their end product biochar for the soil improvement, for the water use efficiency and various other applications. So a lot of work has been done. These are my contributions or my collaborators and our work on that we have published on biochar and heavy metals and some other ways, drought stress mitigation, water use. Some book chapters have been written. Dr. Singh is also co-author in this book chapter, and we discuss some technologies that we studied. This was back in 2014. You might remember you also contributed that. So material has been published, and a lot of information has been made available. I think we should now more discuss about that. We can help them because they cannot follow everywhere because this all material is scattered. Collecting that is very important. And in that visit, there was a visit to the Hard Chemicals in Lahore. They also have seen, and they are practically growing bioenergy crops. Very little research has been done on bioenergy crops and how much calorific value is there. But specifically for the residues we have available, especially the rice crop. But the calorific value of other crops which are becoming popular, like sesame. Sesame is being exported, and a lot of sesame straw is there, and they prefer that because the calorific value of sesame plant is more. Or the energy oilseed crops, they have more potential or they have more calorific value in general. So we can see that from where we can collect the feedstock, and we can also join the people who are taking initiative in the industry, and they are also helping with the farmers. They are helping them collect the material and take to the industry. So rice biomass is you can say is still in demand in energy system, and by that we can get about 18 rupees per kilowatt hour of energy, 18 rupees. So it's very cheaper compared to the, if you know, 1 unit of electricity is how much for residential or for industry it is already higher. So this is a cheaper source of electricity, and the other benefits are associated like water protection and those things. Thank you very much.
So डॉक्टर साहब एक सवाल था, बायोचार की इम्पोर्टेंस के बारे में तो काफ़ी डिस्कशन भी होती रही है, लेकिन इसकी अडॉप्शन टू द ग्रास रूट लेवल अगर मैं बात करूँ फार्मर कम्युनिटी में, शायद इस वजह से नहीं हो सकी कि अवेलेबिलिटी ऑफ बायोचार। सो अभी तक जो लैब स्केल के प्रोसेसेस हैं बायोचार बनाने के वो तो अवेलेबल हैं, लेकिन द कॉस्ट एंड द एनर्जी, द कॉस्ट ऑफ प्रोड्यूसिंग बायोचार राइट नाउ इज हायर देन द वैल्यू ऑफ बायोचार इटसेल्फ। तो आप क्या समझते हैं कि इस बैरियर को तोड़ने का क्या तरीका है? कि एंड दिस इज वन। द सेकंड क्वेश्चन इज द अमाउंट ऑफ बायोचार रिक्वायर्ड पर एकड़ बेसिस टू हैव दैट इफेक्टिव रोल ऑफ इट, जो आप सब बेनिफिट लेना चाहते हैं वो इतना ज़्यादा है। तो इन दोनों इक्वेशंस को हम कैसे बैलेंस कर सकते हैं? ये किस तरह बायोचार जो है अल्टीमेटली फील्ड में आके इस्तेमाल होगी?
Thank you very much for your question. इसमें first question में जो आंसर है वो ये कि we lack technology. So we have always we discussed many times that we should have some prototype, or Dr. Bashir has helped us very much. He has also worked on Bioenergy. They have a plant which is imported from Germany, I think.
We are there.
But now you have manufactured yours, so you got the fabrication technology already. One of the smart kiln that is CC007, that was carbon capture model. Earlier back in 2014 we used that. That is exothermic reaction, and we don't need to use energy. We just need some
Self-sustained.
So for directly producing biochar, it is you can say the cost is like you see the open market charcoal price. That is the average cost, you can say. But in this way, you can process any kind of biomass, whatever you have. Like for our research purpose, like even Government College University, Hyderabad, some researchers they are asking us to produce different kind of biochar. Even the statue shells, they are saying, okay, make us for that, and we want to do some experiment. Almond shells. Peanut shell. So various kind of biomass sources are available, but all of these are scattered. Now with the advent of like the summer season is coming, you will see a lot of supply vendors, and they have huge heaps of the almond shells. So what is the end use of those almond shells? Definitely they will be openly burned, but rather than open burning, if it goes into the cyclic process rather than open burning, this will be beneficial. So in that way, small stoves are also here. We have some small stoves as well. So farmers can, to small extent, they can use with limited oxygen, they can convert that to kind of charcoal and by adding carbon in that. Rather than, because this port towers or post storage, this huge plant, still we are not able to make. So we need big industries like agro to intervene in that if you want to go for industrial scale. But for small scale, definitely we need to go with the new technologies.
Just a thought, CC पे, क्योंकि at the moment there are a lot of biomass being burned. तो जो biomass इसको burn किया जा रहा है in different boilers, उसका जो residue है, उसके ऊपर कोई काम किया जा सकता है, because intermediary process तो हो गया ना. अब उससे आगे अगर हम उस सूट को यूज करके कुछ देख सकें,
that is in highly demanded, that is in very high demand. That ash from the boilers, or this is being used for raising the rice nursery. Rice nursery, when the people rice growers they take it up, when they use ash, they can easily pluck out the nursery small plants, and then they can, and it is also sort of, you can say, nutrients.
So the question was कि हम बायोचार इसलिए प्रोड्यूस नहीं कर पा रहे कि एक तो इसके लिए डेडिकेटेड इंडस्ट्री चाहिए या डेडिकेटेड एफर्ट चाहिए. फार्मर्स वांट टू हैव अ रेडीमेड सॉल्यूशन एट द एंड ऑफ द डे, और वो एक सॉइल अमेंडमेंट के तौर पे अगर आपको उसको देना है तो यू नीड टू हैव इट इन अ वेरी इकोनॉमिकल मैनर के जी 50 किलो का बैग है या कुछ भी. सो पहला सवाल तो ये है कि बायोचार बनाने के प्रोसेस को इतना आसान कर दिया जाए, आइदर या तो इंडस्ट्री इतनी लग जाए वेस्ट टू एनर्जी की कि उसका बायो प्रोडक्ट अवेलेबल होना शुरू हो जाए, दैट इज वन. या जो ऑलरेडी वेस्ट टू एनर्जी का जो सिस्टम या वैल्यू चेन चल रही है उसकी कोई रॉ मटेरियल या उसका जो बायो प्रोडक्ट है उसको किस तरह यूटिलाइज किया जाए.
Definitely, this will ultimately come because energy is, we are in energy crisis. So if we are going ultimately towards reducing the fossil fuel, or we want to go for carbon credit or environmental issues, or we want to curtail the smoke issues, then ultimately we have to come towards this rather than putting 144 ban on various burning points and open burning. Open burning is definitely must be discouraged. Any other question?
Thank you so much, Dr. Farhan, for sharing such a comprehensive explanation regarding the subject. Now, I invite Professor Dr. Muhammad Naveed from Institute of Soil and Environmental Sciences to come here and share his views related to the topic.
अच्छा, मुझे ये प्लान लेक्चर नहीं था क्योंकि मैं बायोचार का कोर्स पढ़ा रहा हूँ सॉइल साइंस में, और तकरीबन मैं काम कर रहा हूँ ड्यूरिंग माई PhD, यानी ये 2009 की बात है, 10 की। इन दी वर्ल्ड अगर देखें तो फर्स्ट जो कमर्शियल यूनिट लगा था बायोचार का वो वियना ऑस्ट्रिया में लगा था, ऑस्ट्रियन इंस्टीट्यूट ऑफ टेक्नोलॉजी। तो 2009 तो मैंने ऐसे जा रहा था तो डॉक्टर जहाज सोया जो है ना, वो उसका मैंने देखा तो वो बैग भरे पड़े थे बायोचार के। आई वाज शॉक्ड क्योंकि पाकिस्तान में अल्लाह उनके जन्नत में जगह है, डॉक्टर खालिद साहब वो बायोचार पे काम कर रहे थे जब उन्होंने कोर्स डिज़ाइन किया था। तो मुझे पता चला कि हम 3 घंटे में कोई 150 ग्राम या 200 ग्राम बायोचार बनाते हैं 3 घंटे में। तो लोकली डिज़ाइन फैब्रिकेटेड यूनिट था, वो 3-4 लाख रुपये का उन्होंने अपनी पैसों से डिज़ाइन किया था। तो मेरे मुंह में पानी आ गया कि इतने बड़े बायोचार के बैग पड़े हैं, वो 50-50 किलो के, 100-100 किलो के। तो मैंने ना जहाड़ से ऐसे बात की कि मैं कोलैबोरेशन करूँगा। मेरा काम एंडोफाइट है, नहीं मेरा काम माइक्रोबायोलॉजी है, लेकिन वैसे बायोचार को देख के, और मैं पाकिस्तान में चूँकि जब मैं PhD करने गया था तो हम लकी डॉक्टर ज़हीर साहब मेरे सुपरवाइजर थे, तो मैं 4 साल के लिए एक लम्हे के लिए भी अपने पेरेंट या मदर इंस्टीट्यूट से डिस्कनेक्ट नहीं हुआ। मैं इसको अपनी गुड लक समझता हूँ या मैं ब्लेस्ड हूँ कि जब मैं वियना में PhD करने गया तो 4 साल मैं हर हफ्ते या हर 2 हफ्ते के बाद मैं अपने सुपरवाइजर के साथ बैठे हैं तो कॉल करके ना सारी अपडेट देता था और सर से अपडेट लेता था UAF में क्या हो रहा है, ISS में, और उधर क्या हो रहा है। तो वो पहला इंस्टीट्यूट वो था बायोलिसिस का। तो मैंने ना 30 kg का यूनिट लिया और $5 यूरो कराया था। तो मैंने 150 यूरो अपने ना स्टेपन से रोका, अपने जो मुझे मिलता था 970 यूरो। तो 150 यूरो मैंने ना बैग उठाया, सारे लोग हंस रहे हैं। एक जो हम करते थे ना ग्रॉसरी, वो ट्रॉली मिलती थी, तो ट्रॉली मेरे हॉस्टल में पड़ी थी, तो मैंने उसके ऊपर बायोचार का 30 किलो का बैग रखा, पोस्ट ऑफिस की तरफ भाग रहा हूँ। क्या करना है जी, 30 किलो बायोचार पाकिस्तान भेजनी है। 2010 लोगों के जहन में नहीं था कि ये भी कोई टेक्नोलॉजी है। तो मैं इतना खुश था। अब 6 महीने बाद मेरी फ्लाइट थी वापस आना, तो मुझे लगा कि बायोचार खत्म हो गई होनी है। तो मैंने फिर एक ट्रॉली ली जहाड़ से आकर, फिर मैंने शोर करवाया कि मैं पाकिस्तान में जाके आपसे कोलैबोरेशन करूँगा, मुझे बायोचार चाहिए। प्रोसेस मैंने सारा समझ लिया था, मैंने कुछ एक्सपेरिमेंट भी लगाए थे। तो उन्होंने भेज दे दिया मुझे कि नवीद ने पता नहीं क्या करना है पाकिस्तान में जाके। वो जो बायोचार बची जो वापस आते, पहले 30 किलो का मुझे नहीं पता था कहाँ गई। एक्सपेरिमेंट लगे होंगे मेरे इंस्टीट्यूट में, अगला 30 किलो मैंने यूज़ किया अपनी तसल्ली से। नहीं, वो जो ग्रामों में प्रोसेस इनिशिएट होता था वो भी पता नहीं ट्रू टू पैरालिसिस था या नहीं था, लेकिन हमने उसको ट्रू टू टाइप किया। खालिद साहब हम हमेशा याद आती है क्योंकि वो अक्सर कहते थे कि मुझे प्रोफेसर बायोचार ने बनाया है। यानी ऐसे पैनल बैठा था, सर कहते कि उन्होंने कहा जी बताएं आपने क्या ऐसा किया कि आपको प्रोफेसर बना दी। तो कहते हैं मैं बायोचार पे बताना शुरू हो गया तो सारी ऑडियंस मेरे मुँह की तरफ देख लिया बायोचार है क्या, और मैं बोलते ही जा रहा हूँ। और एक जब पैनल खत्म हुआ तो उनको लगा, बल्कि जो चेयर थे इंटरव्यू को कहते सर बायोचार के बयान से जिंदा ही नहीं रहना, तो उनको प्रोफेसर कर दिया। तो बड़ा एक लंबी स्टोरी है। फिर मैं जब आया वापस से तो मैंने इसको अडॉप्ट किया इस सब्जेक्ट को और मैंने कमर्शलाइज किया। लेकिन मसला अक्सर अवेयरनेस है, मतलब मैं कंपोस्टिंग रिसाइकलिंग और ऑर्गेनिक वेस्ट पे काम कर रहा हूँ, तो वो मेरे से अगर 500 फार्मर ने कंपोस्ट पे इंफॉर्मेशन ली होगी तो मेरे से सिर्फ 2 फार्मर ने बायोचार पे इंफॉर्मेशन ली। मैंने ये 2000 रुपये किलो था, यानी ये 1800 या 2000 रुपये किलो जरहाड़ सोया से मुझे मिला था $12 यूरो 10 यूरो 180 रुपये का यूरो था। तो 1800 रुपये किलो बना, तो 10 यूरो वो देते थे, उन्होंने मेरे से पैसे नहीं लिए, उनकी मेहरबानी। तो ये वापस आके मेरी कोशिश की कि मैं इसको कमर्शलाइज कर दूँ, इतने बेनिफिट्स थे। और फिर हमने ये यूनिट लगाया था, मैं अक्सर ये इस्तेमाल करता था, बल्कि अभी भी हमारे पास है जड़ा वाला में اور یہ یونٹ کمرشلی ہم نے 100 کلو کیپیسٹی کا لگوایا تھا اور یہ ہم نے یہاں پہ ستیانہ سمندری روڈ سے بنائی تھی یہ ایک لنک یہ ہماری پائرالائسس یونٹ تھی اور ماویلس میں نے اس کے ذریعے 150 روپے کلو باچا کر دی ٹوٹا باچا یعنی 150 روپی وہ جو 1800 روپے تھا وہ 150 روپے کر دیا. لیکن بات پھر ہوئی تھی کہ پاکستان میں جو فارمر کی اکنامک کنڈیشن ہے جو سمجھتے نہیں ہے کہ باچا کی شیلف لائف 100 سال ہے. اگر وہ 25,000 کی باچا ڈال بھی دیں گے تو 100 پہ ڈیوائڈ کریں 250 روپے پر ایئر لگتا ہے. وہ بیچاروں کو کیسے سمجھائیں؟ گولڈ لیف کی ڈبی سے بھی سستی ہے باچا ایک سال کے لیے, تو بڑا مشکل تھا. تو اور دوسرا میرے لیے سب سے انٹرسٹنگ تھا, میں نے ٹریول کیا تو میں سلیکون ویلی ٹریول کیا. اب ساری دنیا میں جو پوٹنگ میڈیا ہے نا, میں نے قطر دیکھا, استنبول ترکی دیکھا, ریاض سعودی عرب, تو مینیور سلری یوز کرتے تھے نا ایئرپورٹ پہ. تو سلیکون ویلی مجھے دنیا میں واحد ایسی جگہ لگی, یہ میں نے تصویر بنا کے سنبھال کے رکھی تھی کہ جہاں پہ پوٹنگ میڈیا جو تھا وہ باچا یوز ہوتا تھا فار لائف 1000 سال کے لیے. اب اس کو کوئی نیوٹن نہیں دے گا, پانی آ رہا ہے بارش کا تھوڑا بہت نیوٹن ریلیز ہو رہے ہیں اور ان کے پودے جو ہے نا وہ یہ دیکھیں, یہ مطلب فار آل لائف کے لیے ہے. یہ مجھے سلیکون ویلی میں پتا چلا کہ واقعی دنیا اکنامکس سلیکون ویلی سے کیوں لینے آتی ہے. آپ کے پاس $10 ملین ہے اور آپ کہیں کہ مجھے ایک سکسیزفل بزنس پلان چاہیے, تو سلیکون ویلی میں جائیں, وہ آپ کو $10 ملین کا سکسیزفل بزنس پلان دیں گے اور وہ واقعی سکسیزفل ہوگا. میں نے جب سلیکون ویلی کو وزٹ کیا, چونکہ میں بایوچار پڑھا رہا تھا, تو کہتے ہیں بہت سارے خوشگوار لمحات میں سے ایک لمحہ یہ بھی تھا جب میں نے بایوچار کا پوٹنگ میڈیا دیکھا سلیکون ویلی میں. تو انٹرسٹنگ ہے, پہلا یونٹ ہم یہ ناکام ہوئے تھے. یہ ہم نے نا جو آپ نے ڈرام والا تھا, فہد صاحب نے بھی کہا کہ ہم ناکام ہو گئے تھے, بایوچار نہیں بنی تھی, اتنا ٹیمپریچر نہیں دیا تھا. 2-3 منٹ میں آپ کو اپنی سکسیس ہوئی ہم کیسے ایوالو ہوئے, اس کو میں نے کیسے 150 روپے کلو کیا 2000 سے. یہ ڈرام تھا تو ٹوٹلی فیل ہوئے. میرے ساتھ نا CS کے آفیسر تھے, ان کو بایوچار کا سبجیکٹ آیا تھا CSS میں, وہ ڈھونڈتے ڈھونڈتے میرے تک پہنچ گئے. شباز علی آج کل پارٹی گیلرت میں شیخپور میں میری اسٹوڈنٹ کو انٹروڈیوس کرا کے بادشاہ پہ کام کرنا ڈاکٹر نویز سے ملے. فیصلہ آباد ان کا ٹرانسفر والا کی جڑا والا میں, تو میرے پاس آ گیا اپنا سارا اسٹال لے کے, سارا انسٹیٹیوٹ پریشان کی اتنی فورس کہاں آ گئی ہے. بہرحال ہم نے یہ مل کے ایکسپیریمنٹ کیا, چونکہ میں کورس پڑھا رہا تھا اور انہوں نے ایسے لکھا تھا CSS میں, تو ہم نے اس کو پریکٹیکل شیپ دے دی. اب یہ ایک ڈرم ہے اور ڈرم میں میں نے اینوبک انوائرمنٹ کریٹ کیا. اس جو چھوٹی ڈرم ہے نا, اس میں چھوٹے یونٹ ہیں بایوماس کے, اور سائڈوں سے ہم نے آگے لگانی ہے تاکہ اندر کوک ہو. لیکن یہ بڑی خوشی, مطلب بڑا رات ہم بڑی خوشی سے کہ ہم نے آگے لگا دی ہے اور صبح جب بایوچار بن جانی ہے. رات ہم خواب دیکھ رہے ہیں جی سویرے پتہ نہیں کی ہو جائے. صبح آگے دیکھا ایسے کا ایسا ہے, وہ جتنی لکڑیاں تھیں نا ویسے کی ویسے پڑی, سارے خواب سوچ رہے تھے کہ پتہ نہیں کیا لے لینا. اچھا یہ پھر ہمیں لگا کہ ہیٹ نہیں بن رہی, انہوں نے ایک ٹاپا بنا دیا کہ اب ہیٹ اندر رہے گی. اگلی رات پھر میں جڑا فیصلہ سے جڑا والا گیا, شباز بھائی اپنے آفس سے اٹھ کے آئے, ہم نے کہا کہ سویرے بایوچار بن رہی ہے بڑے پیمانے پہ, ہم کو بنا رہے تھے جہاں پہ 250-300 گرام. اب ہم نے اس کو سیٹ کو کور کیا, پھر کوئی بایوچار نہ بنے. پھر ڈیزائن ہم آگے کی گیج موٹی, یہاں پہ نا سمندری روڈ پہ لالا رزاق صاحب تھے, انہوں نے ہمیں کہا کہ یہ 3-4 سال کے لیے آپ کا یونٹ ہم بنا کے دیں گے اور جتنا مرضی ٹیمپریچر کر لیں. ہم نے اس کو فکس کیا جڑا والا نے, یہ ٹرینڈ فارم ہے. اب اس کے نیچے آگے لگا رہے ہیں اسمارٹ بایوچار سسٹم. بات بڑی سگیل صاحب کی بات بڑی اچھی تھی, سائنس بڑی کمال کی, اور میں 15 سال سے کر رہا ہوں. کمرشل صحیح چیز ہے, اور کمرشل پھر ہم نے دیکھا کمپیئر کیا کہ بیلنگ, مطلب میں آپ کو چھوٹی سی وہ بھی سکسیس اسٹوری سناؤں گا انڈسٹری میں. تو اس کے نیچے ہم نے مجھے جلانی شروع کر دی. آپ امیجن نہیں کر سکتے اتنا اندر پریشر بنا کہ ہم صبح ایسے, یعنی ہم نا دعا کر رہے تھے یار پتہ نہیں رات کیسے بچ گئے. صبح اندر نا پھر جب اس کو اس فرنس کو کھولا تو اس کا جو باہر کا یونٹ تھا وہ سارا کریک ہو گیا تھا. اندر پتہ نہیں کیا پریشر تھا, کیا گیسز سی بنی تھی, لوکل یونٹ تھا. پھر ہم نے سب سے پہلے اس کے اوپر اگلے دن یہ گیس گیج میجر اور ٹیمپریچر لگوایا تھا. لیکن پہلا جو بیچ تھا ہمارا بڑا ڈینجرس تھا کہ پتہ نہیں کیسے بچ گئی. اگر وہ پھٹ جاتا تو میرے نہیں خیال میں وہ جڑا والا اس فارم میں کوئی چیز بچنی تھی. کہنا بڑا آسان ہے, آپ کو اس گیزا نے ریسرچ سنا دی اور ہم پتہ نہیں کیسے بچیں, آپ کی سوچیں. اچھا یہ اسٹیم نکل گیا, بڑا ایک مار کا پروسیس. میں نے بہت ساری انڈسٹری کو وزٹ کیا, کنونس کرنے کی کوشش کی. 17-18 میں بڑی ایفرٹ کی, کہ نا باہر انجینئر نے تعاون نہیں کیا میرے ساتھ, بڑی ایفرٹ کی. اتنی انڈسٹری کو میں نے ریکمینڈ کی. اب نا وہ آہستہ سے مجھے پیچھے آتے تھے, ڈاکٹر صاحب 25 روپے کلو افغانستان کا کوئلہ ہے, آپ اس چکر میں ہمیں ڈال رہے ہیں, ہم کیوں کنورٹ کریں گے. تو میں 3 سال بعد اسی انڈسٹری میں گیا, تو میں نے پوچھا ہاں جی انجینئر صاحب کوئلے کا کیا ریٹ ہے, کہتے ہیں 165 روپے کلو. تو میں کہا جمہور پٹھی والن دے पट्टी बाल रहे थे। तो शर्मिंदा क्या होता था बेचारे ने। मुझे 3 साल पहले जिसने मुझे बात की थी ना, उसी ने बंदे ने 3 साल बाद उसको मैंने ये कहा ना कि आप पट्टी बाल रहे। तो अगर बायोलॉजी ये स्कीम है इतनी ज्यादा कि आप इमेजिन नहीं कर सकते कि हमें जब बायोचार की ये स्कीम ऊपर पैप लगाना पड़ा, खड़ा नहीं होना था। ये स्कीम वाले को देने जितनी देनी है, आप ऊपर भर नहीं कर रहे हैं, ओपन क्यों करनी पड़ी? आप जो भी करें क्लोज भर नहीं करें, और स्कीम जितनी वाले को देनी देनी। अब ऐश नहीं बनेगी, ऐश बहुत बड़ा प्रॉब्लम है। मैं खुड़े वाला जाता हूँ अपने जड़ा वाला में, ढेर लगे पड़े हैं टेक्सटाइल इंडस्ट्री के बाद। एक आंधी आती है ना तो पूरा खुड़िया वाला में ऐश में डूब जाता है, कोई यूज नहीं। यूज होगा भी कैसे? थक है ना। फासा ने कहा कि नर्सरी ग्रो होती है, हमने जड़ा वाला फार्म में तजर्बा किया, हमारी नर्सरी मर गई, कोई नहीं ग्रो। 4-5% पोटाश होती है, बाकी ऐश है सारी अल्कलाइन है, नेचर है, टॉक्सिसिटी बहुत ज्यादा है, तो कख नहीं होता। मतलब ये सारा कुछ है। तो व्हाई नॉट? वो जो फ्लाई ऐश बन रही है ना, अगर वो पायरोलिसिस स्कीम आपने बॉयलर को देनी जितनी मर्जी दे रही, लेकिन जो बायोमास बने वो फ्लाई ऐश ना बने, वो बायोचार बने। तो ये 17 की बात है, मैं इंडस्ट्री के पास लेके गया। तो डॉक्टर साहब ने बड़ी बात की कि हमें अपने रिसोर्सेज से करना पड़ता है, इसमें कोई शक नहीं है, लेकिन बहुत सारे अच्छे बंदे भी इंडस्ट्री वाले पैसे दे देते हैं, मुझे बहुत सारे सिलसिले में उन्होंने पैसे दिए। तो ये यूनिट देखेगा, ये स्कीम है बेसिकली। वो जो डॉक्टर साहब ने 3 साइंस दिखाई है, मैं आपको ट्रू टू टाइप पिक्चर दिखाना चाह रहा हूँ। साइंस पढ़ी है, इसमें मैंने लेक्चर वो खोला तस्वीरों वाला जो मैंने किया, तो सर ने लेक्चर दिया ऐसे डॉक्टर साहब। मैं आपको बता रहा हूँ हमने कैसे किया। वो स्टीम जब तक 150 डिग्री तक टेम्परेचर जाएगा, आपकी स्टीम इतनी ज्यादा आप इमेजिन नहीं कर सकते, जितना देना एनर्जी वाले को दे दें। 400 डिग्री टेम्परेचर हमने फिर लोड किया। अब 400 डिग्री आप देखिए, थोड़े से कैरी वेपर्स आ रहे हैं, लेकिन हमारी गैस पे ये देखिए स्टीम रुक रही है ना, ये फ्लेम चलना शुरू हो गया अगेन। अब जैसे जैसे प्यूरिफाई होगी गैस, अब किसी बाकी गैस हो गया, हमने इसको कंडेंस भी किया, एग्जैक्ट 2-4 मिनट के बाद प्योर फ्लेम आ गया। आपकी सोच इतना कमाल का फ्लेम था कि अब इसको मुसीबत इसको कैसे सामने, पहले हम स्टीम को देख रहे थे कैसे मैनेज करें, अब फ्लेम को मैनेज किया हमने। वो स्मार्ट बायोचार सिस्टम पे आ गए कि इसका पाइप लगाया और अपनी आग बंद कर दी और इसके पाइप को ले लिया। बड़े खुशी हुई कि चलो हमारी लकड़ियां तो बंद हो गई ना, क्योंकि लकड़ियां बड़ी जल रही थी पहले। ये फ्लेम हाइड्रोजन गैस बड़ी कमाल का फ्लेम। अब इसको हमने 2 ड्रम लगाए, कंडेंसेट किया, इसको प्यूरिफाई किया, कोई ऐसी साइंस नहीं थी, लेकिन ये हम उसको रीसाइकिल कर रहे हैं ड्रम के साथ। पहले एक ड्रम में पाइप गुजारा, जितने वेपर्स थे, जितनी इंप्योरिटीज थी वो कंडेंसेट हो गई क्योंकि ठंडे पानी से गुजारा। फिर आगे एक पाइप को हमने दोबारा गैस से मैंने कनेक्ट कर दिया, ये आपको दिखा रहे हैं यहाँ पे, जहाँ पे हमारी आग साहब है। ये फ्लेम था ओरिजिनल, अनबिलीवेबल फ्लेम। जितने मर्जी सिलेंडर पर रहे, जो मर्जी का, इसके जैसी एनर्जी मैंने नहीं आज तक देखी। मैंने रसोई गैस भी देखी, हमारी सारी एनर्जी देखी, लेकिन ये अनबिलीवेबल फ्लेम था, इतना बायोगैस से जो। और हमारी जो सक्सेस स्टोरी थी, मैं भी किताबें पढ़ाता था, बायोचार के ट्रायल करता था, लेकिन ये चूंकि सामने सारा चल रहा था, सारी फिल्म घूम रही थी ना, होना कैसे, और बड़ी मुश्किल बचे। अब फ्लेम और ये कैरी वेपर सभी हमने जमा कर रहे थे, जिराड सोया सेपरेट नहीं कर रहा था ना, सेम गैस में कैरी वेपर को मिक्स ही हो रहे थे। हमें खुशी थी कि जो 2010 में मैं रिएक्शन लेके आया था, मैंने तीनों चीजें सेपरेट कर दी। कैरी वेपर्स को हमने नीचे रखा जी, अब ये सारे वेपर्स दे रहे हैं, अब फ्लेम बढ़ता जा रहा है। और ये कैरी वेपर्स, आपकी फर्नीचर इंडस्ट्री की इतनी डिमांड है, आप सोच नहीं सकते। ये वाइट गोल्ड है, बाचार तो बहुत दूर की बात है, ये 3 चीजें हिंट कर ले तो ये तो प्रॉफिटेबल है। मैंने तो बाचार को 150 किलो का बनाया, तो ये तो 2 चीजें आ जाएंगी। ये पेंट इंडस्ट्री बहुत कमाल, और फर्नीचर इंडस्ट्री आपकी सिंक लगती है, जब ये होता है हाइड्रोकार्बन की पावर है, सिंक नहीं लगेगी। इतना कमाल का जो वाइट गोल्ड है। अब डीजल को तो छोड़ दें, डीजल में तो बहुत कॉस्ट पड़नी है ना, इसको अपनी लोकल इंडस्ट्री को देने जितना देना, लेकिन कंट्रोल नहीं हो रही थी सिंक गैस। कभी हम गीला मटेरियल मिट्टी मल रहे हैं, कभी गोबर की वो दे रहे हैं, अनबिलीवेबल फ्लेम था जी ये। तो ओरिजिनल ट्रू टू टाइप बायोचार बनी, और ये 100 किलो फीडस्टॉक की 36-38 किलो बायोचार बनी, और इतनी खुशी कि 250 ग्राम जब हम बनाते थे 12 में। फिर 2014 में एक प्रोजेक्ट में हमारे पास वो जर्मनी की फर्नेस आई, तो 1.5 किलो बनने लगी, वो भी मेरे पास है, वो चल रही है फर्नेस, और ये 40 किलो तक बन गई। तो खुशी की इंतहा नहीं कि जराड सोया से मिलते करके 30 किलो दी थी, तो ये 40 किलो का हमारे पास 3 साल बड़ा यूनिट बना था। तो मैं इसको चलाता रहा, फिर हमने ग्राइंडिंग यूनिट भी लगा हुआ हमारे पास, बड़ा कमाल की शाइनिंग थी। ये कोयला हम यूज करते रहे इसको। जहाँ पे सनावला साहब का लॉन्ग टर्म ट्रायल लगा रहे थे, मुझे कहते 150 किलो 200 किलो बायोचार दे दो। 150-200 कहाँ से आनी है, इस प्लांट से आती रही है ट्रू टू टाइप, लेकिन एक स्टेज पे आके वो पीछे पड़ गए। मैंने कहा अब मुश्किल है, अब हम उसको नहीं दे रहे। लेकिन ये शाइन, ये कंट्रोल ऑफ ऑक्सीजन, जब आप जितना ऑक्सीजन को कंट्रोल कर लेंगे ना ओपन बर्निंग से ये क्लोज बर्निंग, उतनी कोल पे शाइन बनेगी। आप ऑक्सीजन जीरो कर दें, इतना फाइन मटेरियल, इतना शाइन है आप इमेजिन नहीं कर सकते। ये एक सिंपल सी तस्वीर है, ये मोटले फॉर्म से ये शेप है। तो इंटरेस्टिंग है, लेकिन कॉस्ट इस तरह, मतलब बहुत सारे मैं बॉयल इंजीनियर से मिला, लेकिन अफसोस हुआ कि मुझे इंडस्ट्री ने इतना नहीं किया। फिर हमने खुद ये सारा अपने पैसों पे डिज़ाइन किया था, जो सब 10 लाख रुपया तक हमने खर्च किया था 2014-15 में ना, 16 में। तो इंडस्ट्री अल्टरनेट आ गई। जड़ावाला में कोई टेक्सटाइल की बात कर रहा हूँ, डॉक्टर साहब ने कहा ये कंप्रेसर बेस हमारा जो कोई के साथ कुछ कंसल्टेंट फार्मर का, तो कोई के साथ हमारा जो एग्रीमेंट हुआ कोई टेक्सटाइल, ऐसे बॉयलर आ गए सर कि वो कोई CO2 जाती नहीं एटमॉस्फेयर में, स्क्रबर लगे हुए हैं। और पाकिस्तान में जो एडवांस इंडस्ट्री है वो बॉयलर जर्मन टेक्नोलॉजी है, जो स्क्रबर है कोई जीरो गैस नहीं जा रही, फिर ऊपर बर्निंग क्या होगी। तो मैं कभी कभी कहता हूँ कि शायद बायोचार कमर्शलाइज मुश्किल हो, क्योंकि ऐसी टेक्नोलॉजी आ गई है कि आप लो क्वालिटी फीडस्टॉक को बर्न कर सकते हैं। तो कोई उनसे जो हमारा एग्रीमेंट हुआ डॉक्टर साहब, उन्होंने हमें कहा जी कि हमें एक क्वार्टर के लिए 30,000 टन मटेरियल चाहिए, एक क्वार्टर, साल का चौथा हिस्सा या तीसरा हिस्सा, तो 30,000 टन चाहिए। तो हमने 6 बेलर लगाए जड़ावाला में, सरदार बाबर साहब उनके फॉर्म में गेंदा बेलर चल रहे हैं। तो 1 एकड़ से 2 टन मटेरियल इकट्ठा होता है सर, 50 मन 40 किलो 50-500 का 20 2 टन, एक राइस का फील्ड हम हार्वेस्ट करते हैं तो 2 टन मटेरियल। तो सरदार साहब ने कहा जी डॉक्टर साहब 30,000 टन है, 2 पे डिवाइड करें 15,000 एकड़ है, तो मैं 15,000 एकड़ का बायोमास इकट्ठा करूंगा तो एक क्वार्टर का फीड स्टॉक पूरा होगा कोई नो टेक्सटाइल का। तो अब कोई नो टेक्सटाइल जो ना 1 टन यानी 1 एकड़ के लिए हमें 30,000 देता था, तो इसका मतलब 15,000 का टन 15 रुपए किलो, यानी हमें 1 एकड़ की इकट्ठी करते थे 2 टन। 2 टन का कितना पैसा मिल रहा है 30,000 का मतलब 2 पे डिवाइड करें 15,000, तो 15,000 रुपए का 1 टन मटेरियल मेरा जो 15 रुपए किलो है, कोई कॉस्ट नहीं है। कोयले की कीमत जो मुझे कहते थे 25 रुपए किलो मिल रहा है, वो अफगानिस्तान से आ रहा है, वो 165 रुपए चली गई, और फीड स्टॉक हम 15 रुपए दे रहे हैं, तुक्के सबसे महंगे मिल रहे हैं, 3 रुपए किलो दिख रहा है तुक्का, उसका बड़ा अच्छा फ्लेम है। तो जितना 15 रुपए किलो 6 बॉयलर लगा के वो कोई लाहौर में है, उनकी जर्मन टेक्नोलॉजी है। हमने क्या किया कि फार्मर हमें खुद बुलाया, तो हमने 30,000 में से 15,000 फार्मर को देना शुरू कर दिया। 15,000 खुद रखा, अपने जो पैसे रखे 15,000, उसमें हमारी कॉस्ट कितनी थी 4,000 रुपये या 5,000, 10,000 बचा। तो हमारे ट्रैक्टर डेली जो लग रहे हैं ना, डेली भी हमने कोशिश की, तो कोई 150 दिन में हमने कोई न्यू टेक्सटाइल का 1 क्वार्टर का वो ऑर्डर पूरा किया। 125 दिन समथिंग 4 महीने लगे, लेकिन उनको ऑर्डर इतना था। तो एडवांस टेक्नोलॉजीज आ गई है, रिसर्च के लिए बायोचार बड़ा अच्छा है। इसको प्रीशियस जब तक वो तीनों इसके बायो ऑयल कमाल है, सिन गैस कमाल है, बायोचार एज ए बाई प्रोडक्ट चलेगा तो बात बनी है। अदरवाइज एनर्जी के लिए बड़ा इकोनॉमिकल आ गया, जो मैंने बता दिया, दुनिया कन्वर्ट हो गई। हमने बायोमास की फ्यूल पैलेट बनाई। तो मेरे पास ना कुछ साल पहले एनर्जी डिपार्टमेंट किया कि आप हमें ना कुक कर दें, टोरीफेक्शंस कर दें। मैंने टोरीफेक्शंस की इतना मुश्किल हुआ, तो उसने मुझे एनर्जी की डॉक्टर अजहर साहब थे, तो उनके वाले साहब बॉयलर इंजीनियर भी थे, तो मुझे था मैंने कहा डॉक्टर साहब की काम किया था, इतना महंगा साड़ा भी जोर आया, आपने वो पैलेट बनाई, कॉस्ट बनी, तो मैंने उनको फ्यूल पैलेट अपनी ढाई, मैंने कहा कि देख लो दोनों पे चला के अगर इसकी और फिर वैल्यू कम हो तो मुझे पकड़ लेना, कॉस्ट इससे आपके कई गुना कम है। तो टोरीफेक्शन से हमने डायरेक्ट फ्यूल, वो जो पैलेटिंग थी ना डेंसिफिकेशन से, उसकी वैल्यू भी ज्यादा थी या उसके बराबर थी, और उसकी कॉस्ट कई गुना कम थी। सब्जेक्ट बड़ा इंटरेस्टिंग है, कार्बन क्रेडिट एडवांस कंट्री में। अब एग्रो ने पहला सेमिनार करवाया था सेंसिटाइज करने के लिए कार्बन क्रेडिट में। अगर कार्बन क्रेडिट आ जाता है तो फिर ये आपको अच्छा इकोनॉमिकल बन जाएगा, अदरवाइज अभी इसमें रिस्क लेने की जरूरत है। मैं रिसर्च नहीं कहूँगा, रिसर्च को छोड़ दें, क्योंकि मैं पिछले 15 साल से रिसर्च कर रहा हूँ, तो रिस्क लेने की जरूरत है। आप जितना रिस्क लेंगे फिर ये फील्ड में जाना, अदरवाइज नहीं जाना सर। थैंक यू वेरी मच।
Now I would like to invite our chief guest, Professor Dr. Zahid Ahmed Zahid, to come on the stage and share concluding remarks and brief all the participants as well as our resource persons.
Assalamualaikum, Dr. Farooq. It's nice to see you after quite a long time. Desi Saab, Shahid Saab, Ashraf Saab, Fahad Saab, and dear students. It's my pleasure to be present here today. And it was quite a very good experience listening about a very holistic talk from Dr. Saeed. It was really very much, you can say, informative. And then Dr. Fahad discussed the practical aspects of using biochar. And finally, Dr. Naveed, he spoke very good and shared his experiences. We always appreciate him in doing such sort of experiences, but of course we always advise him to move with a little bit slower speed. So much high speed is not good for research also. But anyway, we still appreciate his efforts. I'm thankful to the Agro Fertilizers for arranging this excellent talk and provided opportunity to the students and the scientists for sharing this wonderful information. And I would also endorse the comments from Gadesi Saab that the technology is good, but the economy is the issue. And I do remember one Congress of the Social Society of Pakistan. I was perhaps chairing that session, and it was Dr. Balwant Singh from Australia. He was presenting a talk on this biochar, and finally the issue was, rather the conclusion or the take-home message was the same, that it is a very good buzzword for seeking funding, but its practical application still needs a lot of work to do to make it economical. So let us see what happens in future. But of course, the avenues are opening up, and things are getting comparatively easier now. And we need to motivate the farmers for adopting this technology. Once the technology is adopted, it automatically gets cheaper. So if there is the demand, and I believe that the scientists will be compelled to make it economical, as Dr. Naveed shared some of his experiences. I'm also thankful to Agro Fertilizers for providing me the opportunity to share a few words with you. I don't want, of course, to go into the details of the biochar because 3 speakers have already said a lot, but still I'm really thankful to the honorable speakers and the organizers for providing this wonderful opportunity. Thank you very much.
Thank you so much, dear audience. Now we are moving towards our last segment, that is souvenir distribution. For souvenir distribution, I would like to invite Head of Astronomy Department, Sayyid Shaudab Sanjay to come here. Deputy Manager, Dr. Sayyid Shahid Hussain from Agro Fertilizers, and Mr. Imran Ahmed, Research and Development Officer, Faistabad, Professor Dr. Zahir Ahmed Zahir, Dr. Farouk, Ex-Director, Jutha, please come on the stage. Now I would like to invite our first resource person, Dr. Muhammad Sadeed, to come on the stage and receive token of appreciation from Agro Fertilizers. Now I would like to invite Dr. Fahad to come on the stage and receive this token of appreciation from Agro Fertilizers. Professor Dr. Zahir Ahmed Zahir. audience. Now please, we will gather in front of this building for a group photo.
जी सर
फाहद के